Good morning.
Good morning. What's all this? Your results. Congratulations to all. I am confident you'll all achieve your goals. So, young man, what are your aspirations?
I want to do robotics, ideally from the Bust Institute in the US.
And you, young lady?
Sir, I love kids and I would love to learn pediatrics. I feel Boston is the best place for that.
Sumit, what about you?
Back home to India for medicine.
Good. I'm sure you'll all achieve your aspirations, be it in India or anywhere. Keep in mind, your first challenge is the entrance, whether it's IIT, JEE, SAT or NEET. You have to learn from the masters. Brilliant Qatar is the passport to your success.
We undertake coaching for regular and repeat batches and tuition for board examinations. Brilliant Education Centre, Doha, Qatar.
Yes, it's ready, sir.
Good evening, everyone.
Good evening. Hi.
Welcome to Brilliant Qatar Maha Marathon YouTube live for grade 12 physics, day 1.
So already, I think, sir, many students are waiting. Yes. Good evening,
Okay,
Atul,
yeah.
Tanvi. Yes. Many are there.
Good, 51 students. I
Salman.
think online.
Okay. Very good.
Thank you. Yes. As we know, we are in the last lap of our revision, and we started this revision process long back, step by step. And we started MCQ revision long back, and we have completed that unit-wise MCQ revision very effectively. And you all many of you attended those live streaming sessions, and those videos are still available in our channel. You just go and watch anytime you want. So the whole syllabus MCQ discussion is available for all subjects. So right now,
So
physics,
today's session, we are not going to discuss any MCQs because it is already discussed. We are going to focus on, that 2 mark, 3 mark and 5 mark.
Yes, exactly.
Yeah, this is what
because MCQs, that's why I told you right in the beginning, MCQs, we mostly, there are 2, 3 marks and 5 marks, of course, those questions are included in this discussion because MCQs are already we have completed. You can go, it is there in our archives, go and watch those videos.
So many are there. Satwik, Abdul Aziz, King Paper, Afan, Rudya, Ramanujan. Okay, good evening all of you.
Thank you.
Yes.
1 or 2 more points before going to start discussion. We are just 2 days away from our physics exam, and our revision class are also going parallel to this, right? So we have completed almost all the syllabus in these 2 days. We had a quick revision of basic concepts, even higher order thinking questions separately, and you all were attending the same sessions also. So today we plan to discuss only volume 1 textbook because you will have a different, individually our revision plans will be different. Of course, your revision will be special for you, and you will have a particular order. You will like some chapters and you prefer some chapters. At least we hope the part 1 revision in these 2 days you have completed successfully, so that this discussion will help you to understand what is going on, what happened in the past 5 or 10 years paper, for 2 marks, 3 marks and 5 marks, a complete analysis of that syllabus, part 1 textbook syllabus, except EM waves, right, sir?
Sure.
So from electrostatics till alternating current, we go for this, in this discussion. And tomorrow we'll go from electromagnetic waves till the semiconductors. That is the second part of this live, tomorrow at the same, at 5 p.m. only. And see, in this discussion, we are mainly focusing these things, like identifying the hot spots in each chapters. But we have a complete analysis of each chapters that you can see during the discussion. From that, we can identify what are the hot regions, hot spots in every chapter where we have to focus more, so that repeatedly long answers, 3 marks, 2 marks are repeatedly coming from that section.
Chapter-wise analysis.
Exactly. So that is what we are going to do in this discussion. One thing, followed by the probable questions, right, sir? So we have past paper question collection, right? Yes, and we'll be going through that. See, we know exact questions may not be repeating, but we have
same
similar type of questions repeating, in different papers. If you go through the past papers, you can see that. So that also we will do. Then
And another important area, this graph type and circuit analysis question.
Exactly. So that we kept till the last part of the discussion. After completing each and every chapter discussions, we'll go for a separate discussion for important graphs and devices questions. because that is one of the most confusing part, like for most of us. And also predicting long answer type questions, that is definitely the section, like, long answer. We have 3 5-mark questions, and each and every chapter we identified some topics, like, so from that we will be predicting some long answer questions that you must revise before you go. Okay. So anyway, I think without wasting time, we can go straight to the questions. Students are also waiting for the same. So over to you, GB sir.
Okay.
So can you continue?
So before that, let's explain. This one is, this is a syllabus only, CBS board syllabus. I mean, this is till unit 4 only we are going to discuss today. So you can see 16 plus 17. So total like 33 marks we are going to cover in today's discussion. That means almost 50% of the total syllabus. All right, so we are not wasting time. We are going to start with our first chapter, electric charges and fields. So before starting the questions, let's have a quick analysis of the topic from this chapter. This is the analysis of last 10-year questions. You can see that it's like in this chart, you can see how many MCQs, how many 1-mark question, 2-mark question, which is asked from each of the topic. So I'm not going to explain each and everything, but you can see, dear students, the area where most of the questions came from the first chapter is, you can look at this part. This part is an highlighted part. So you can see the graph. That is 10th point. What is the 10th point? It is Gauss theorem and its application. So by analyzing the last 10-year papers, you can see that the most of the question, almost 60% of the question from the first chapter, electric charges and fields, came from the Gauss theorem area. Of course, other topics also there are questions. So please keep this in your mind, especially this area. More question means you can see the long answer question. How many long answer question came from Gauss theorem part? Applications of Gauss theorem, there are 3 probable 5-mark questions. So please be focused on that area in this chapter. So now we are going to start with our first question, and please respond when I'm discussing, or we are discussing each and every question. Take a paper instead of simply watching it. Be a part of the discussion. Try to do it by yourself within that short time itself, and you can comment your answers. It is not like watching a movie, like your brain should work. Like, let us explore this and be ready. Let's be ready for the exam. So question number 1. Given a uniform electric field E is equal to 5 into 10 power 3 I cap Newton per Coulomb, find the flux of this field through a square of 10 centimeter on a side whose plane is parallel to YZ plane. What would be the flux through the same square if the plane makes a 30-degree angle with x-axis? So by reading this question, if you got an idea that this is a question from, direct question from which topic? It is from electric flux. Hope all of you know this concept clearly. What is electric flux definition? Just try to recall everything related to this. What is electric flux? Total number of field lines passing normal to a surface. And what is the formula for electric flux? You know that the formula for electric flux is E dot A, which is EA cos theta. So let's check the question now. It is a uniform electric field. What is the magnitude of that electric field? It is 5 into 10 power 3 I cap. So from that I cap itself, you can understand the direction of this electric field is along the positive x direction. So E is equal to, I am writing the magnitude here, E is equal to 5 into 10 to the power 3 is the magnitude. Direction, you know, it is I cap means positive x direction. Find the flux of this field through a square of 10 centimeters. So we need to find the flux passing through a square of side 10 centimeter on a side whose plane is parallel to YZ plane. So the plane of the square is parallel to the YZ plane. So let's draw the situation. See, this is x-axis, positive x-axis. This is positive y-axis. This is positive z-axis. So where is that plane? The plane is parallel to YZ plane. Which is a YZ plane? This is a YZ plane. So parallel to that means the plane we can show it is like this. So we need to find flux passing through this square. And what is the side of that square? It is given as 10 centimeter. It is in YZ plane. What is the direction of electric field? Direction of electric field is given. It is along positive. So it's a very simple question now. What is the formula? Phi is equal to EA cos theta, E dot A, EA cos theta. You can comment your answers. Comment your answers. Most of you might have got the answer now. So substitute, it is 5 into 10 to the power 3. That is E value. Area, what is area? It's a square. Square side is 10 centimeter. Given it is in centimeter, so please don't forget to convert into meter. So 10 centimeter means you know that it is 10 into 10 power minus 2 meter. That means 10 power minus 1. Squaring we get what? So area will be side square L square, so it will be 10 to the power minus 1 square, we get 10 raised to minus 2. That's the area, alright. So what we get here, into area is 10 to the power minus 2 cos theta. Cos theta, be careful students, what is the value of theta in this formula? You know that it is the angle between vector E and vector A. What is the direction of vector? It is area vector. Yes, I can see the answers, I can see the comments from many students. Yes, so this is the area vector. What is the angle between A and A? It's 0, cos 0 is 1, so we get 5 into 10 power 3 and then so it will be 50, very good, 50 Newton meter square per coulomb. Alright, yes, Smriti, Shazar, Satvik, keep going. So there is one more question here. What would be the flux through the same square if the plane makes an angle 30 degree? 30 degree with the x-axis. Plane is making 30 degree with x-axis. So how can you do that? That means if this is x-axis, plane is making 30 degree. Let it be the plane. So plane is making 30 degree with x-axis. So the area vector will be like this. Yes or no? If this is the direction of area vector, then what will be the angle between x-axis? That means electric field and area vector, it will be 60. Yes or no? Now, second answer. So this is the first one. The second answer, how can you find? EA cos theta. EA is already 50. What is cos 60? 1 by 2. So we get 50 by 2. 50 by 2. Very good. Very good. Tanvi, Said. Yes, flip-flop, Karthik. Very good, dear students. So please keep electric flux. Let them ask any question. We will answer it. Calculation of electric flux, because we know the formula. We know how to take the value of theta and all. Okay. So can I go to the next question with your permission? Here, we are trying to cover total 100 questions by today and tomorrow. 50 questions today, 50 questions tomorrow. That's what our plan. And apart from this 100 question, we will be showing you the main focus area, like long derivations, 5-mark question, everything will be showing here. So without wasting time, I'm going to the next question, question number 2. Look at this. A particle of charge 2 microcoulomb and mass 1.6 gram is moving with a velocity 4 I cap meter per second. At t is equal to 0, the particle enters in a region having an electric field E equal to 80 I cap plus 60 j cap. Find the velocity of the particle at t is equal to 5. It's question with, you can see that we need to apply some more basic idea, then only you can solve it. Listen carefully, not a tough one, but you have to use some fundamentals of physics. Let's check what is the meaning of it. A particle of charge 2 microcoulomb and mass 1.6 gram is moving with a velocity of 4 I cap. So initially that particle has a velocity. But what is its direction? It is I cap is there, which means the direction of that initial velocity is along positive x-axis. It is entering, at time t is equal to 0, the particle is entering in a region where there is an electric field. But check the direction of electric field. That electric field is 80 I cap plus 60 j cap, which means that electric field has both the components, x component, x direction is there, y direction is also there. Find the velocity of the particle. What is happening here? What is the idea? They are asking initial velocity is given, what is the final velocity? Basically this is the question. Initial velocity is given, what is the final velocity? If initial velocity is given and asked final velocity means, what is the basic method? You know that we have to use equations of motion. Which formula? One of the basic equation in kinematics, motion in a straight line, you know that V is equal to U plus AT. That is the formula we are going to use for this. V is equal to U plus AT. Here, initial velocity is given, time is given. So which is the missing factor, students? It is acceleration, yes or no? So you have to think, how can you find acceleration based on the given data? Once you get the acceleration, this is a simple question. So let's analyze again. Electric field is there. What is the charge? Charge is 2 microcoulomb. You know that when a charge is entering or placed in an electric field, it will experience a force. Our first step is finding that force using which formula? F is equal to QE. F is equal to QE. All of us know this formula. F is equal to QE. Now let us substitute this. F is equal to, what is Q value? Q is 2 microcoulomb. That means 2 into 10 to the power minus 6 into electric field is given 80 I cap plus 60 j cap. 80 I cap plus 60 j cap. So expanding this, we get 2 into 80, 160 into 10 to the power minus 6 I cap plus 120 into 10 to the power minus 6 j cap. J cap. So we got the force. But again you can see this force has two components. I cap, that means along x direction there is a force, along y direction also there is a force. So I can write this force as Fx, F along x axis, because I cap is there. And this is the force along y direction. So Fx is equal to 160 into 10 to the power minus 6. And like that we can find Fy also. So please understand, what we need is, we need acceleration. We need acceleration. So how to find acceleration? You know basic formula for forces, F is equal to ma. So we got force along x axis. So this force you can write it as what? M into ax, because F is equal to ma. So max is equal to 160 into 10 to the power minus 6. Then from this you can easily find ax. It will be 160 into 10 to the power minus 6 divided by mass. Mass is given as 1.6 gram. So 1.6 gram means into 10 to the power minus 3. Yes or no? Yes. Now we need to solve. We can find its acceleration. So this will become 160 divided by 1.6 into this minus 3 will go up. We get 10 to the power what? Minus 3. Okay, so 1.6 by 1.6, it will be 10 to the power minus 1. This is the acceleration along which axis? X axis, 10 to the power minus 1. So that part is clear. In same way you can find acceleration along y axis as well. But before that, let me show you how to find the final velocity. What they are asking? Final velocity. It's a 3-mark question, dear students. So there will be some steps. Okay, so by seeing this, don't be confused. Read it carefully, you can do it. So V is equal to U plus AT formula. If I am applying, I can write Vx is equal to Ux plus Ax into T. Vx, because basic formula only, V is equal to U plus AT. Now what is Vx? Initial velocity along x direction. You can see the question, it is 4I cap. So initial velocity has only x component. So that is 4 plus, what is acceleration? Acceleration is 10 to the power minus 1. That means 0.1 into what? Time. What is the time? Time given as 5 seconds. So we got the answer. Look at this, 4 plus 0.5, 4.5 meter per second is the velocity along which axis? It is the velocity along x axis. Understood or not? Please comment. Is it okay? Yes. Now we need to find acceleration along y axis. For that you can write Fy. What is Fy value? Fy is 120 into 10 to the power minus 6. 120 into 10 to the power minus 6. I am leaving this rest of the calculation for you because I hope you got the idea. Yes or no? Yes or no? Can you do the y component? But please note that if you are getting acceleration here, Vy is equal to Uy plus Ay into T. Ay into T. But what is Uy value? What is Uy value? Check the value, 4I cap meter per second. Initial velocity direction is only along x axis. That means there is no initial velocity along y direction. So in this case you need to take it as what? 0. Got it? Yes. Then acceleration you can calculate. I'm not making the calculation here because it will take a lot of time. We need to cover as many topics, as many questions as possible. I hope it's fine. And finally, one more thing, how can you write the final answer? That's also very important. We will get Vx value, like that you can find Vy value, and final answer you have to write like this, Vx into I cap plus Vy into J cap. It should be the final way of writing the answer. Clear or not? Please comment. Is it okay? Can I go to the next? Comment, then only I can go to the next. I hope everything is fine. Yes. Thank you, Salman, Naship, and Atul. Yeah. So I'm going to the next question, question number 3. Look at this. 2 point charges of plus 1 microcoulomb and plus 4 microcoulomb are kept 30 centimeter apart. How far from plus 1 microcoulomb charge on line joining the two charges will the net electric field be 0? You know, this is a repeating question. You are familiar with this question, I am sure. But don't make silly mistake for these kind of question. The point only we need to find. So this is one of the repeating question, one of the simple question from this chapter. Finding the point where the resultant field or resultant force is 0. So what is the logic of this question? Check. You can do along with me and comment your answers. Plus 1 microcoulomb is kept. Plus 4 microcoulomb is kept here. at a distance of 30 centimeter apart. So first thing you have to check whether the point where the field is 0 will be in between these two or outside. So both are positive charge. Both are positive charge means if you are assuming this is the point where the resultant field is 0, as per the definition of electric field intensity, you know that it is the force experienced by a unit positive charge. So you can keep a +1 charge here. So this is positive, this is positive. The field will be like this. And the field due to this one, this is positive, this is positive. So they are oppositely directed. So if the directions are opposite, if their magnitudes are equal, then surely the field will be 0. So you can just equate the magnitude of electric field. So field due to this one, I am writing it as E1. If that E1 is equal to field due to the second charge, that will be the point. So for that you can assume this distance as x. If this is x, what will be the remaining distance? It will be 30 minus x. Quickly do it. What is formula for field? K q by r square. So k, this is q1 by x square will be equal to k q2 by, this will be 30 minus x the whole square. Answer, you can comment your answers please. Yeah, I can see they are 10 centimeter. Yes, fine. So q1 is 1 micro by x square is equal to q2 is 4 by 30 minus x the whole square. So before squaring this, before expanding this, try to think about the possibility of taking square root. Here you can take, because 4 root will be 2, so we get 1 by x is equal to 2 by 30 minus x. 2 by 30 minus x. Solve it easily, you'll get x is equal to 10 centimeter. Yes or no? Yes. 10 centimeter from 1 microcoulomb charge. Don't make mistake for this type of question. Here you can see both are positive. What about if one is positive and other is negative? And they're asking identify the charge. Sorry, identify the point where the field is 0. If one charge is plus and one charge is minus, then the point will not be in between, it will be outside. So you need to take an outside point and take the distance from both the charges, equate the field. Method is same, but you have to analyze whether the charges are like charges or unlike charges. Can I go to the next question? Can I go to the next one? Yes. Yeah, Satvik, very good. Correct. Question number 4. Look at this. A question from Gauss theorem. Question from Gauss theorem. You are familiar with this question. This question is asked in 2018. Check this. Read it carefully. Define electric flux. Is it a scalar or a vector quantity? That's the first question. Define electric flux. You know what is the definition of electric flux. Is it a scalar quantity or a vector quantity? Quickly comment it. Flux is scalar or vector. You know that electric field intensity is a vector quantity. Area vector, it's a vector quantity. But what about flux? It's a dot product. E dot A. It's a scalar quantity, isn't it? Yes, it is a scalar quantity. A point charge q is at a distance of d by 2 directly above the center of a square of side d as shown in the figure. Use Gauss law to obtain the expression for the electric flux through the square. You're familiar with this question? In all of your classes, this question I have discussed. See, there is a square. The side is given as what? D. At a distance of d by 2, there is a charge q. Then what is the flux through this? What is the idea of this? They are asking use Gauss theorem. You know that to use Gauss theorem, we need to construct a Gaussian surface. And what is the nature of, what is the property of Gaussian surface? Gaussian surface is a closed surface, isn't it? So we need to make it as a closed surface. This is not a closed surface, it's an open surface. So make it closed. Yes, I can see the answer. Very good. I can see the answers. So to make it closed, I'm just closing it like by making it as a cube. Now it's a perfect closed Gaussian surface. So what is the flux through this Gaussian surface? You know that as per Gauss theorem, the total flux phi is equal to 1 by epsilon naught times the net charge enclosed. So 1 by epsilon naught times q. This is the total flux passing through this entire Gaussian surface, that cubical shape. But they are asking what is the flux through this square, that one face. So you know that a cube has how many faces? 6 faces. So what is the flux through one of the face? Simple. So you can divide it by 6. So we get phi through 1 square. That means one face is q by 6 epsilon naught. Got the answer now? Very good. I can see many students are commenting as Hridya, Tanvi, Azim. Very good, dear students. Keep going. You guys, I'm sure you guys will create history in this year exam. Okay. Next. There is a sub question. So this is clear. So 5 by 6 epsilon naught. If the point charge is now moved to a distance d from the center of the square and the side of the square is double, explain how the electric flux will be affected. Don't skip the sub question. Okay, you have to, when you are answering a question, you have to make sure that you are answering to all the questions they are asking. Look at this. If the point charge is now moved to a distance d from the center of the square and the side of the square is double. So if this is a square, side is double means this side is double, this side will also be double. So the total square will be becoming like this. And the charge is moved from this point to this point. So again, if you are considering Gaussian surface, it will be something like this. So what is the net charge again? Net charge inside that Gaussian surface will be Q only. So again, we will be getting the same answer. So what is the answer? Very good, not affected. Ashmita, very good. Yes, king paper ball, I can see a name, nice name. Ansh, no change, very good. So the flux remains the same. Flux. So when you are applying Gauss theorem, so there are questions like what happened to the flux when the radius of the Gaussian surface is doubled, when the radius of Gaussian surface is halved. Like that questions you can see when you are applying Gauss theorem. Students, please note that we need to consider only the net charge enclosed by the Gaussian surface. Okay, so clear. So I am going to the next question now, question number 5. Look at this. Two identical point charges Q each are kept 2 meters apart in air. A third point charge Q of unknown magnitude and sign is placed on the line joining the charges such that the system remains in equilibrium. Find the position and nature of Q. Position and nature of, I think, position and nature of capital Q only we need to find, not small q. So find the position and nature of Q. So let's check this question. Let's check. Two identical point charges. Q and this is another Q. 2 meters apart. So this distance is given as 2 meters. 2 meters. A third point charge Q of unknown magnitude or sign is placed in the line joining. So we don't know where that charge is placed. The line joining. So let us assume I am going to place the charge over here. Q. Okay. Charges such that the system remains in equilibrium. System remains in equilibrium. For the system to be in equilibrium, find the position and nature. They are not saying that a charge is in equilibrium. What is the meaning of equilibrium? You know that equilibrium means the net force acting on that particular object has to be 0. So here if you are saying if this Q is in equilibrium means you need to concentrate only on that Q. The net force acting on that charge will be 0. But in this question they are saying that the entire system is in equilibrium. What is the condition for that? For a system to be in equilibrium, the force acting on each of the charge, like force acting on this one must be 0, this one must be 0, this one must be 0. Then only we can say that a system is in equilibrium. So let me take the equilibrium condition for this one first. Let me begin with the equilibrium condition for this one. So for the net force on this to be 0, there will be two forces on it, one due to this Q and one due to this Q. For that force to be 0, you can understand the force will be oppositely directed. What can you say about this distance? If I am taking this as x, at what point if I am placing that charge, the net force will be 0? Can you comment? Can you comment? If x is equal to total distance is 2 meters, for the net force acting on this charge to be 0, where should I place it? That means x value will be, yes Smriti, right. For force to be equal, there are identical charges on both sides. So the force to be equal means it should be placed at 1 meter middle. So there is no doubt about that. It should be placed at the middle. Then only the force on that charge will be 0. So we get x is equal to 1 meter. Do you have any doubt about that? If any confusion, you can equate. But actually that's a simple logic. Now, if the charges are not equal, then how can we do that? I can explain you. There will be force between this charge and this one. I can write k into q by x square. I'm just showing it actually. This is very simple. Kq by x square is equal to the force between this and this. So that will also be k into qq by, what will be that distance? 2 minus x the whole square. Solving, you can easily see that x is equal to 1 meter. But actually no need to do this. It's just a matter of using common sense. The charge has to be where? At the middle. That means we got the value. The position is what? 1 meter. Is it clear? Yeah. But they're asking the nature as well. Should it be a negative charge or a positive charge? This one you need to be careful. Position for this particular question, finding position is easy. How can we find the sign? For that, if you are taking only the equilibrium condition of this charge, if it is a positive charge or it is a negative charge, anyway the net force on that charge will be 0. But you just think about the equilibrium condition of this one. This one, be careful. This is Q, this is also Q. That means they are identical charges. It's given in the question, they are identical. So if identical means like charges, what will be the nature of force between this charge and this charge? It will be repulsive. So the force between this and this will be towards left. Repulsion. This will be repelled and this will also be repelled in this direction. That means for that charge to be in equilibrium, that repulsive force should be balanced by a force by this charge. So we need a force in this direction. Then only the net force on this charge will be 0. Got an idea? So for that, now you can tell me what should be the sign of this one. I need a force towards this direction. I need an attractive force. So what should be the charge? Comment it please. Negative, yes. The sign will be negative. Then only we will get a force in this direction. Yes, yes, yes. Hisham, right answer. Very good, dear students. So position is 1 meter and the sign is what? Negative. All right. So I am going to the next question now. Question number 6. This is a repeating question. I think you are familiar with this question. Let's check it again. Two small identical electric dipoles, A, B and C, D. Each of dipole moment P are kept at an angle of 120 degree to each other in an external electric field E pointing along the x-axis as shown in the figure. Find the dipole moment of the arrangement and magnitude and direction of the net torque acting on it. So two questions are there. So before starting this question, let's quickly revise. What is a dipole? It's a pair of equal and opposite charges. What is dipole moment? Dipole moment is the strength of a dipole. It's a product of magnitude of charge and distance between the two charges. And what is the direction of dipole moment? Very important. What is the direction of dipole moment? It's a vector quantity. You know that. Direction of dipole moment is from negative charge to positive charge. And what is dipole moment formula? Magnitude of charge into distance between the two charges. Then torque. Torque is when you know that a dipole is kept in a uniform electric field, it will experience torque. If it is kept in a non-uniform electric field, it will experience both force and torque. Keep all these ideas in your mind. And what is torque formula? P cross E, P is sine theta. Yes or no? And along with that only we studied about potential energy. Potential energy formula is minus P cos theta. Just for your information, potential energy is minus P cos theta. Torque is P sine theta. Now let's check what they are asking here. Two small identical electric dipole A, B and C, D. Check. A, B. Where is A, B? This is A, B. In the diagram you can see A, B is like this. Other dipole is CD. Where is CD? Yeah, this is CD. CD. They are kept at an angle of 120 degree each. In an external electric field E pointing along x-axis. So this is the direction of electric field. It is directed along positive x-axis. What is the first question? Find the dipole moment of the arrangement. So first question is you have to find the dipole, the net dipole moment of this arrangement. So here two dipoles are there. Two dipoles are there, A, B and C, D. You know that dipole moment is a vector quantity. So if two dipoles are there means how can you find the net dipole moment? Take their vector sum. So for that you have to be careful about the direction. Let's check what is the direction of dipole moment of AB. AB is arranged vertically. What is the direction of dipole moment? It is from negative charge to positive charge. Negative charge is here, positive charge is here. That means that dipole moment direction of the first one will be upward. I am taking it as P. P. Alright. What is the direction of the dipole moment? CD. CD you can see negative charge is here, minus Q plus Q. So the direction will be this way. That is also same, P only. Magnitude is same. And this angle is given as 120 degree. 120 degree. You can comment your answers. You can comment your answers. So 120 degree. So two vectors acting at an angle of 120 degree each. Directly applied vector sum formula. P net dipole moment is equal to root of, what is the formula for sum of two vectors? A square plus B, root of A square plus B square plus 2AB cos theta. So what we get? Root of P square plus P square, because both are identical. 2AB, 2P into P, again 2P square cos 120 degrees the angle. What is cos 120? Cos 120 you know that it's minus half. So 2 will be cancelled. P square minus P square cancel. We get square root of P square. That's again P. Again P. So the result of this question is P itself. P itself, the resultant dipole moment is P. Got it? So please don't be confused with the angle. This is 120 degree. Cos 120 is minus 1 by 2. So the answer is P. Resultant dipole moment is P. Now second question. Magnitude and direction of the net torque. Net torque. That means we found the net dipole moment, then net torque. So what is the net dipole moment? P itself. So net torque, how can you write? Directly you can write Pe sin theta. This is the formula for torque, magnitude of torque. Okay, so P is P itself. E is given as E only. They did not give any magnitude, so we can keep it E. Now the only confusing part here is what is theta? In this formula you know that theta is the angle between vector P and vector E. Vector P and vector E. What is the direction of vector E? Vector E is along positive x-axis. Okay. Now we need what is the direction of net dipole moment. Net dipole moment means one dipole moment was in this direction. You know that one is this way. Other dipole moment is this way. What is the direction of the resultant? If two equal vectors are acting at a point, what will be the direction of their resultant? Two equal vectors, two equal forces are acting at a point means the resultant direction will be, it will bisecting, it's through the middle. So surely the direction of resultant will be like this. So in this diagram I can show the resultant dipole moment will be like this. It will be bisecting these two. What is this total angle? 120 degree. So it will be through the middle. So this will be 60 degree. That means what will be the angle between this dipole moment and this electric field? This is 90, this is 60 means this angle will be 30 degree. Understood or not? 30 degree. Okay, so angle between electric field and dipole moment is 30. So we can write it as PE sin 30. Sin 30 is 1 by 2. So look at the answer. It is PE by 2. PE by 2. Clear or not? So the magnitude of the resultant torque acting on this point is, acting on the dipole is PE by 2. Okay, but the question is over? No, they are asking direction. My dear students, please don't skip anything, because if you forget to write the direction, you may lose 1 mark. So be very careful. Magnitude and direction of what? Direction of the net torque acting on it. So how can you find direction? This is very simple here. You know, this is torque is actually P cross E. P cross E. Cross product direction. You can easily use screw rule or thumb rule. So here, what is the direction of P? P is in this way and E is this way. So you can keep our right hand like this. So it has to rotate in this way. So you can check your thumb. The thumb will be inward. Inward means it is which axis? Can you comment? This is x axis. It is y axis. Outward is z axis. So here the direction of the torque is inward, into the plane. Can you comment? What is S? And yes, Z means which Z? Like positive or negative? It is negative Z axis. Ruben? Yeah, correct. Right answer. Very good. It is negative Z axis. So that is the direction. Clear? So please practice if there is any confusion. 1 or 2 times you just go through it. So I am going to the next question now. Question number 7. Question number 7. Look at this. No need to worry. Like some students will have worry about by seeing the length of the question. The question may be very lengthy, like you need to read lot of things. Be calm, read it carefully, you can solve it. An electric field is uniform and acts along positive x direction. The region along positive x direction in the region of positive x. In the region of positive x. It is also uniform with the same magnitude but acts along negative x direction in the region of negative x. The value of the field is E equal to 200 Newton per Coulomb for x greater than 0 and E equal to minus 200 Newton per Coulomb for x less than 0. A right circular cylinder of length 20 cm and radius 5 cm has its center at the origin and its axis along the x-axis, so that one flat face is at plus 10 cm and the other is at minus 10 cm. Find the net outward flux through the cylinder, the net charge present inside the cylinder. Okay, so here what you have to notice, again a question based on Gauss theorem. I told you the importance of that topic at the beginning. There are many questions they will ask from this topic. So here what is happening? There is positive x and negative x. So let me draw that situation first. Let it be the x-axis. X-axis. Okay. Now, there is electric field. There is electric field in both the direction. You can see along positive x direction there is electric field. It is given 200 Newton per Coulomb for x greater than 0. X greater than 0 means positive x only. Minus 200. So don't be confused. So if this is the y-axis, there is an electric field like this. It is 200 Newton per Coulomb. There is an electric field like this, which is also 200 Newton per Coulomb. Its direction is minus. That's why negative comes there. Okay, and after that what we are doing, a right circular cylinder of length 20 centimeter. So there is a cylinder of length 20 centimeter, radius 5 centimeter, center at the origin. Okay, center at the origin, and its axis is along x-axis. So axis is along x-axis means the cylinder is placed like this. Cylinder is placed like this. Okay, so that one flat surface is at x is equal to 10 centimeters. So simply confusing. Okay, this is 10 centimeter. Flat surface is, one flat surface is x is equal to plus 10 centimeter. Other one is at minus 10 centimeter. My dear students, please don't be confused. This is a very simple question actually. So you just analyze the question and understand what is the meaning. So everything is fine. Now what they are asking, net outward flux through the cylinder. That is the question. So you know the flux formula. Flux formula is EA cos theta. Yes or no? So here you can see, since the electric field is along x-axis, that field will go through this direction. The field is going through this direction. It's not have any component along y-axis or z-axis. That means no flux will be passing through the curved face of the cylinder. The flux will be passing only through the end phases. Understood or not? And here you can see the direction of area vector. Area vector direction is outward normal. So here the direction of area vector will be towards right. Here it will be towards left. So in both the cases you can see the angle between electric field and area vector is 0. So they are in the same direction. So cos 0 is 1. That means here you can see the flux will be EA. Here also you can see the flux is what? EA. Both we need to add. So the flux will be 2 times EA. 2 into EA. This is what? The calculation is very simple. 2 EA. Got it? Now you just substitute. I hope till this it is clear, no? Is it okay? So it is 2 into, what is E value? E is 200. E is 200 into area. Area means area of this n phase only. You just leave the curved surface. Length of the cylinder doesn't matter. You know that it's a uniform electric field. Check the area. How can you find length? Radius is 5 centimeter. So if it's circular, so radius means pi r square. So pi into 5 centimeter. 5 centimeter you can convert. So 25 into 10 to the power minus 4 you will get. Okay, so 2 into 2, 4, 4 into 25, 100. So we get 10,000 into pi into 10 to the power minus 4. So 10 power minus 4 and 10,000 will be cancelled. Pi means 3.14. This is the answer. Newton meter square per coulomb. This is the answer for the first question. Is it okay? Please comment. Please comment. Clear or not? See, look at the how many line is there for that question. But answer is just like you can find in 4 steps. So this is what, it's mainly how you are approaching a question, how you are understanding a question. Is it clear or not? Comment. Yes, fine. Next is, after getting the first one, look at the second question, the net charge present inside the cylinder. Okay. Net charge present inside the cylinder. So how can you find the net charge after getting flux? Now you can directly apply what? Gauss theorem, phi equal to 1 by epsilon naught into what? Q. So what we get? Tell me. Q is equal to epsilon naught into phi. So epsilon naught is 8.85 into 10 to the power minus 12 into what? Phi. What is phi? Phi is 3.14. You can multiply. I'm not going to multiply here. I'm not wasting time. Is it okay? Is it okay, dear students? Please comment. Yes. Fine. I hope everything is fine. Yes, Ruben, Ashmita, Hisham, Tanvi, correct. Okay. So I'm going to the next question. Question number 8. Again, a question based on flux, electric field. A uniformly charged large plane sheet has a charge density. Again, look at this. Look at the length of the questions. Very big, but don't worry, again easy question. A uniformly charged plane sheet of as a charge density sigma equal to 1 by 18 pi into 10 power minus 15. Find the electric field at a point A, which is 50 centimeter from the sheet. Okay, so first question is they're asking what is the electric field. You know application number 2 of Gauss theorem. What is the electric field due to a plane sheet of charge? E is equal to sigma by 2 epsilon naught. This is the formula for electric field due to a sheet of charge. Okay, so here it is given what is the field at a distance of 50 centimeter. Do we have to check or do we have to apply that distance here? You know that the field is independent. The field is independent of what? The distance. So just substitute. Sigma is given 1 by 18 pi. 1 by 18 pi into 10 to the power minus 15. This is sigma value divided by 2 epsilon naught. 2 epsilon naught. 2 epsilon naught. So we can write like this. Divided by 2 epsilon naught. Okay. Now we need to solve this. How? Can we make it in the form of 1 by 4 pi epsilon naught? Yes. So here you can write 18 as what? 2 into 9 pi, and then there is epsilon naught. Okay, into 10 to the power minus 15. So there is 1 by 4 pi epsilon naught in the denominator, and there is a 9 into what? 10 to the power minus 15. Now what is 1 by 4 pi epsilon naught? It is 9 into 10 power minus 19 divided by 9, okay, into 10 to the power minus 15. So 9 got cancelled. Sorry, 9 into 10 to the power 9. Sorry. So it is 9 into 10 to the power 9 divided by 9 into 10 to the power minus 15. Okay, so 9 got cancelled. The answer is 10 to the power minus 6. That's it. 10 to the power minus 6 is the answer. 10 to the power minus 6. Yes or no? Yes. Now, look at the second question. Consider a straight line. Yeah, Ash, right answer. All of you please comment. Tushar is asking, sir, I have a doubt in the previous question. Can you please explain why we won't take the negatives? Previous question means this question, Tushar. Like you know that negative here, both E and area are in the same direction. So if the question is like there is a cylinder and then electric field is coming from this side and it is going in this way, then only one flux will be negative, because electric field direction and area vector direction will be opposite. So cos theta will be 180 degree. Here you can treat like two independent situations. So it is going this way, area vector is also. If area vector direction also, we need to take negative if you are thinking like that. If electric field along negative direction, if you are taking negative, area vector direction will also be negative. Both will be negative. So final flux will be what? Positive. I hope it is clear, Tushar. Okay. Yes. So consider a straight line where you can see PQR, place 50 cm from the charge sheet on the right side as shown in the figure. At which of these points does the magnitude of the electric field U2 sheet remains the same as that at point A and Y? Can you answer this question? So they are asking here, there are 3 points, P is there, Q is there, R is there. We got a field at the point A. Out of these 3 points, at which point the field will be same as that at A? P, Q, R. Can you comment? Can you comment? At A some field is there. So out of these 3 points, at which point? Everywhere it's same like that. One answer is there. Any other answer? Same everywhere. Fatima is saying same everywhere. Everywhere. Okay. But there is a problem, dear students. Why I can understand your way of thinking, that you are saying that it is independent of distance. So all are along that, so the field has to be same. But what you have to note here is, this sheet is not an infinite sheet. This sheet is up to this point only. Okay, that means the point P is at the edge, R is also at the edge. So at the edge, what is happening means the field will not be uniform, it will be curved. Why means, why if there is a charge like this, charge distribution is like this, at this particular point, assume this is a sheet, there will be fields due to this one, field due to this one. So the resultant field will be like this. That's why we are getting what? Horizontal direction. Okay, but at the edge, it won't be like that. There is no vector to cancel it, which means if it is not an infinitely long sheet, we cannot say the field will be same here and here. So what is our answer? Our answer is, yeah, Satvik, the field will be like curved at P and R. So the answer will be Q. Q is the right answer for this question. Okay. Now there is a sub question for this. Two small identical conducting spheres carrying charges 10 and minus 20 when separated by a distance r experiences a force F each. If they are brought in contact and then separated to a distance r by 2, what is the new force between them in terms of F? Again a force question. Let me erase this one. I think all of you noted the answer. 10 power minus 6 is the answer. So let me quickly do the Next question, please check. Two small identical conducting spheres. So two small identical, that's very important here. One is 10 and other is minus 20. When separated by a distance r, experiences a force F each. So if you are taking the distance of separation as r, F is equal to, what's the formula? K into what is Q1? Q1 is 10, Q2 is 20 by r square. This force is given as F. Now what is the next question? If they are brought in contact and the separated to a distance of r by 2, what is the new force between them? Brought in contact, what will happen? The charge will be divided, like, so one is how much? 10 and other is minus 20. So 10 plus minus 20 will be what? Minus 10, that will be equally divided. So the charge on the spheres will be 5 and 5 now. Understood? Minus 5 and minus 5. So what will be the new force? F dash is equal to K into 5 into 5 divided by, the distance is reduced to what? R by 2, the whole square. It is R by 2. So we get 25K divided by R square by 4. So 4 will go up. So we get 100K by R square. 100K by R square. Now you can check here, what is K by R square? This K by R square is here, no? That K by R square is F by 200. So that you can substitute. So 100 into F divided by 200. That means we get F dash is equal to F by 2. F dash is equal to F by 2. Very good. Karthik, Satvik. Yes. Correct. Logic is very good. So I think that is also very clear for you. So I hope all the questions which we discussed, so just practice it. Important questions only discussed from this chapter. Now let me show you one of the direct question which you are not supposed to skip. You have to go through it. Two electric lines cannot cross each other. Also they cannot form closed loops. Give reason. I'm not answering this because you know this, but why I'm showing this one is don't skip these type of question. You have to go through this because they are repeating questions. Look at the next one. A point charge is kept in the vicinity of an uncharged conducting plate. Sketch the electric field lines between the charge and the plate. So what is the charge? It is plus Q. There is a plate. So you know that due to static induction, negative will be induced here. So the field lines has to be like this. So please go through this question. Next, obtain the expression for the electric field at a point on the equatorial line. Equatorial line and axial line derivation. Important. You have to study. Okay. Next. Derive an expression for the electric field with a dipole on perpendicular bisector. Expression for electric field equatorial line. Find the resultant electric field due to an electric dipole. Same question. So dipole field torque. Stable equilibrium, unstable equilibrium. You know what is stable equilibrium? Stable means theta is 0. Unstable equilibrium means theta is 180. So go through these questions. Expression for the torque. Derivation of torque may come for 3 mark. Okay. This is Gauss theorem. Application, that special case 2 plate. Go through it. Direct question. We are not discussing direct question here, but you have to go through this repeating question. Again, Gauss theorem application. Spherical shell. Gauss theorem application, spherical shell. So these are the main areas from this chapter. Again, spherical shell question. So look how many times these questions been asked. Okay. So I am going to leave for a short time. Now we are going to start our second chapter. Potential and capacitance. Over to you, Sunil. It's actually like students are responding very quickly. But
that was an interesting one, sir, and very informative too. Yes, guys, keep commenting and be with us. And for the next couple of hours, we are going to do the whole part 1, as I told you right in the beginning. Electrostatics is now, the first chapter is over. We'll quickly go through the second chapter too now. Okay. Like an overall revision of the important concepts. See, electrostatics 1, even GB sir correctly said that long answer questions that you have to, must revise. These long answer questions, you don't have to skip. I have to repeat the same thing what GB sir shared. Like, you have to revise those because the 3 marks and 5 marks, right? Those long answer question sessions, we have a correct idea about the questions, like what are the types of questions we get, which are the topics, from which questions are repeatedly coming. So we have a strong hold on that particular session. So don't lose even a half a mark in that particular session. Fine. Okay. Anyway, let's move on to that capacitance part, potential and capacitance. chapter. We have some 8 or 9 questions from that also to discuss. Before going to the questions, like we have done in electrostatics 1, like charges and field, that chapter, potential chapter is also like analyzed here based on the past papers. You can see these bars, like they are the number of questions. You can see the number of questions on the left side, and these are the topics. 1 to 13 topics are listed on the left side. Okay, you can see those topics, starting from electric potential till energy stored in the capacitor. So where we get frequent bars, that means we get frequent questions from that part. That's the meaning. Okay, so based on that, we have to focus those particular topics, and we have to revise them properly. We have to make them perfect. Looking into this 4, 5, 6 and 7, these topics we get repeating questions, and interestingly all types of questions. See, long answer questions. You can see this, the red one is going to be like MCQs. We got recently MCQ questions, and this pink one is going to be very short answer question. Then short answer question, that is going to be 2 marks. Short answer question 2 is going to be 3 marks, and the lightest, that light gray is going to be long answer questions or 5 mark questions. So when we go through this, we can see this part. See, so many people are there, right? So we see repeating question from this part. Let us check what are those topics. 4, 5, 6 and 7. 4 is potential due to a system of charges. See, potential due to a system of charges. We know electric potential, when we keep them, when we keep 2, 3 charges, we started with potential due to 2 charges, right? Then we explained what happens, we add 1 more charge, then adding 1 more charge, a system of 4 charges, what will be its potential energy, how it can be calculated, that kind of questions. We have examples coming up, and that kind of questions we get from topic number 4. But 5 is equipotential surface. Equipotential surface is a small topic anyway. We get repeating questions from that part. Okay, so make sure properties of equipotential surface, how to draw equipotential surface for a given situation, like point charge or charge distribution and so on. Just revise that particular topic. 6th is potential energy of a system of charges. Fourth one was potential due to a system of charges. Sorry, 6th one is potential energy of the system of charges, and 7th one potential energy in an external field. Like that is the first part of that chapter from which we get repeating questions. And you can see the last part of the chapter is actually from capacitance. 10th onwards. Actually 9th onwards it is capacitance, then parallel plate capacitor. See, we can see all types of questions from that particular topic. See, 11th is effect of dielectrics and parallel plate capacitor. So potential due to system of charges, potential energy of the system of charges, and capacitance. See, from those topics we get questions very frequently in the last 10-year papers. Okay, let's see. Now we'll move on to the questions. Question number 1 from this one, and we have altogether around 50 questions to finish from all these chapters. Okay, so the first 8 questions were from first chapter. Now the next 8 will be from second chapter, and we have to finish these 50 questions for up to induction and AC. Fine. N small conducting liquid droplets, each of radius r, are charged to a potential V each. Okay, see, conducting droplets. Fine. These droplets coalesce to form a single large drop without any charge. Without any charge leakage. That means we are going to combine all those small drops to make a big drop. Yes. Find the potential of the large drop definitely in terms of potential due to a small drop. We got potential of each small drop is V. Okay, let's see. We had N identical drops. See, small drops, and each of them have a potential V. Okay, so we can say each of them are charged by Q, and these small drops have a radius R, so that what will be the potential V? See, what are the concepts related? Potential on the surface of a charged conductor. What is the expression for potential due to a charge on the surface of a charged conductor? We know potential V is going to be equal to KQ divided by R, right? Where R is the radius of the conductor. Find conducting sphere. The question is based on that particular concept, right? So V is equal to KQ by R. This is the potential due to each and every, like out of that N small drops, each and every drop has this much potential, KQ by R. Okay, so what we do with these small droplets, we combine them to form one single drop. That one single drop will have a radius capital R, because we are going to combine all the drops, right? Yes. See, potential of this big drop, let me take it as some V dash or something. Okay, V dash is the potential of the big drop. We have to find out what is V dash in terms of V. V is the potential due to one of the charge, I mean one of the small sphere, right? Yes. Okay, so let's move on. What will be the total charge in the big sphere? What will be the total charge? How many small drops we combined? N, as per the question, capital N is the number of drops we used. So we can say each of them have a charge Q, right? Each of these small drops has a charge Q. Therefore, total charge on this sphere, the big drop, is going to be N times Q, correct? And its radius is going to be R. Therefore, V dash, potential of the big drop, is going to be K into charge on that sphere, conducting sphere, divided by its radius, capital R. Now in the next step, we will get the answer if you substitute what is the value of Q and what is the value of capital R. Value of capital Q, we already got it from this. So I am going to substitute K times N into small q divided by R. Now we have to substitute, capital R, substitute for capital R in terms of small r, so that KQ by that small r can be taken as small v. We will get V dash in terms of V finally. Okay. For that, we did this kind of questions in different context, right? So we know when we combine the small drops to make a big drop, volume remains the same, correct? Volume is a constant. Volume is a constant. If volume is a constant, volume of the big sphere 4 by 3 pi into capital R cube is equal to total volume of this fluid, like that particular droplets, right? That means 4 by 3 pi into small r cube is the volume of one single drop, and we have n times such small drops. We can see 4 by 3 pi r cube can be, 4 by 3 pi can be cancelled from either side. What will be r if you take the cube root on either side? R is equal to n raised to 1 by 3 into small r. See, we have capital Q substitution already we have done. Now we have to substitute for capital R, right? So let us put this value of R in this equation. That is our final answer. Let's see, we can say V dash, the new potential of the big drop, is equal to K times N into Q divided by, see, instead of this R, we had to write N raised to 1 by 3 times R, right? And I'm going to just rewrite this equation as KQ divided by R. Now we have one N in the numerator. N raised to 1 by 3 in the numerator comes up, it becomes N raised to minus 1 by 3. So that KQ by R is nothing but potential of the small drop, correct? And now what is N into N raised to minus 1 by 3, right? So it is going to be N raised to 2 by 3. So we can say V dash is going to be, this part is V, so V into N raised to 2 by 3. That is the final answer. Okay, so concept was related to potential due to a conducting sphere, right? We know potential inside is going to be a constant, and that is equal to the potential on the surface, right? The potential on the surface, we had the equation V is equal to KQ by R, where R is the radius of that spherical conductor. Fine, I hope you got it. Yes, Smriti, Hisham, Ashmita. Yes, many of you already answered that question. So not only just the question, the concept is clear, I hope. Moving on to the next one. Yes, again another basic question, like 2-point charges Q and minus 2Q are kept at a distance d apart. Find the location of the point related to the charge Q at which potential due to this system of charges is 0. See, potential due to a system of charges. That is one of the important topic that we mentioned when we analyzed the chapter, right? Potential due to a system of charges. We are given two charges here. One is a positive charge, which is plus Q, and the second one is a negative charge, which is minus 2Q, right? Minus 2Q. They are separated by a distance, capital D, small d. That is what given in the question. Yes, D is the distance. You are asked to find from that positive charge Q plus Q, how far is the point where total potential is 0. Yes, so we know what to do for these kind of questions. You're given a distance D, we will assume a point like point A or something. where potential is going to be 0. How many potentials available at the point A? 2 potential due to a system of charges, right? We know equivalent potential at the point A is sum of potential due to both the charges. Yes, exactly, right. So we can just take this distance as x, because in the question you are specifically asked to find the distance from where? Relative to the charge q. So from charge q I have taken the distance x, so that what is the value of x is going to be the final answer. Yes, and this distance can be d minus x. Now it is easy, right? So how can you find it out? We know total potential at A is 0. Total potential at A is going to be 0. So what? So we can say V1 plus V2 at A should be equated to 0. How will you find V1? V1 is KQ divided by R. What is the distance R from the charge to the point A? That is x plus, see, when you calculate the potential, we consider the sign of the charge. Unlike force and electric field, we know, right? Being a scalar quantity, the sign is important. So we can say K into minus 2Q divided by the distance is now d minus x. That is equated to 0. See, we can say KQ by x is equal to, see, that minus sign is there, so I am taking that into the RHS so that we can cancel some term. K into 2Q by d minus x. Yes, yeah, yes, Kavi and Ayash, so many of you, Satvik already solved the question, so we know KQ can be cancelled from either side, correct? So we have 1 by x is equal to 2 divided by d minus x. So cross multiply, we get d minus x is equal to 2x. Taking x to the other side, it becomes 3 and LHS is d. Finally, what is your x? X is equal to d by 3. Yes, so the question was based on the concept of system, potential of a system of charges. We had 2 charges in this case. We calculated total potential. Unlike the calculation of total force or total field, we don't have to go for vector analysis or something, right? Because potential is what? Potential, that was the only thing that we liked in the calculation of potential. We know, yes, potential is a scalar quantity. So we just go for the like scalar, just some of their magnitudes, considering the sign, of course, and that is what we did. Okay, fine. Moving on to the next question, number 11. Right, regarding electric dipole. See, by the way, one thing I have to mention, like, you know, as for the long answer questions, all derivations, even I will go for that long answer questions at the end of this discussion of this chapter. I will say that at that time. But anyway, I remind you something. Dipole derivations, all dipole derivations, like what is potential due to dipole, what is axial line electric field, equatorial line electric field, torque acting on a dipole, potential energy of a dipole, everything, all those derivations you must, okay, revise properly, and they are important. Let's go for this question now. We have an electric dipole of dipole moment P. Yeah, luckily we don't have any numerical values. Fine, P is the dipole moment given, is initially kept in a uniform electric field E such that P is perpendicular to E, right? So we have an electric field, uniform electric field E, and we kept a dipole in this case, like, you know, this is the negative charge and this is a positive charge of the dipole. See, this is how I kept it. We know direction of dipole moment is always from negative to positive. See, that dipole moment is perpendicular to E. Yes, this is the initial position of the dipole. Now let us continue. Find amount of work done in rotating dipole to a position at which P becomes anti-parallel to E. If you want to make P anti-parallel to E, your P should be lying in this way, right? Yes. So initially, what is the angle between dipole moment and electric field? Theta 1. Initially, it is 90 degree. When you keep your dipole like this, so that P is anti-parallel to electric field, angle between P and E, theta 2 changes to what? 180 degree, right? Yes. Yeah, yes, exactly. First is 90, yes, first is 90. Second one, like the second angle I am talking about, that is, yes, 180. And we know the equation, potential energy, work done is nothing but potential energy of the dipole. We know 2 equations, like, you know, one is in terms of theta 1 and theta 2. Like whenever you are given 2 angles, we have to go for that, and this is an example for that. So we can go for U is equal to PE, dipole moment into electric field, cos theta 1 minus cos theta 2. Good. Yes, someone commented that equation also. Yes, Mohammed Zabi. Good. So U is equal to PE into cos theta 1. Theta 1 is 90, so it's going to be 0 minus cos theta 2. This is theta 2. Right, theta 2 is 180, so minus 1. So we get just PE. That is your energy, right? Work done or potential energy of the dipole. That will be equal to work done. So electric dipole moment and angle between electric field and dipole moment, its direction, all these concepts are required to solve the question. Equation is this, and it's easy. Let's move on to the next. Question number 12. Yeah. Define equipotential surface. Yes, I told you that was one of the important topic, right? In that like analysis part, I told you equipotential surface is a very small topic, but still we get repeating questions from that part. What is an equipotential surface? When can you say a surface is equipotential? If potential is same everywhere, right? Correct? Or if you given a surface and the potential is same everywhere, that is said to be an equipotential surface. We know surface of all conductors are equipotential. Fine. So we defined equipotential surface, that we know. Then the next question is to draw equipotential surface. I told you this, right? So we have question to draw equipotential surface for some given cases. The case 1, in the case of a single point charge. See, first one is a single point charge. So if I consider a single point charge kept in space, see, there will be electric field around it. We know electric field around it, and that electric field is directed radially outward in all directions if it is a positive charge, or radially inward if it is a negative charge. Okay, so this is the direction of electric field. You're asked to draw equipotential surface. See, we know shape of equipotential surface. Can someone tell me what is equipotential surface, shape of equipotential surface for a point charge? Yes, delta V should be 0, exactly. Concentric circle, Ashmita Chakrabarti, yes, concentric circles. That concentric circles, when you draw, one more thing you have to remember. See, look at one of the questions coming up later. Why the equipotential surface about a single charge are not equidistant? So when you draw the diagram, you should be very careful. This is my first equipotential surface about around the point charge, right? The next one will be somewhere here. And the third one, keep, the shape is perfect sphere. That is how you have to draw. Okay. So the spacing is increasing, right? Their separation. This is not the same as the second one. And the third one will be even further. Spacing is increasing, right? It is not equidistant. That you have to be careful. Luckily, we have a question mentioning that below this. Okay. So for the point charge, we already have this potential surfaces. The second question was about in a constant electric field in z direction. We know, yes, that also we are getting answers here. We have to go for uniform electric field, and in uniform electric field, we know equipotential surface is always perpendicular to the normal to the feed line, right? Or feed line should go perpendicular to the equipotential surface, we know, right? That is one of the properties of equipotential surface. Wherever you go, see, this will be perpendicular only, feed line. So here, if you want to draw, you can go for planes, right? Perpendicular planes. In the sense, if this is z-axis, this should be in xy, xy plane. Yes, so when you draw these equipotential surfaces, here you have to keep this separation constant, like same. Whatever distance between these two, the same distance you have to maintain for the second also. Why? We are coming to the answer for that question. Why it is not equidistant here, and why it is equidistant in the second case, right? Yes. So we are coming to that only. I'm going to explain the same concept. So why this is not equidistant, and why this should be equidistant between law. So that is the next question. We are coming to that question only now. Why the equipotential surface about a single charge is not equidistant? Okay. So you can see on the board we have the equipotential surface diagrams. They are not equidistant because according to the property of equipotential surfaces, the relative separation, the separation between equipotential surfaces represents relative strength of the electric field. Wherever electric field is stronger, your equipotential surface should be closer to each other, they should be closer. If electric field strength is weak, equipotential surface should be further away. When you go away from the charge, what happened to the electric field? Electric field decreases. Correct? Electric field decreases. So the separation should increase because we are going to a decreasing electric field region. But in uniform field, right? A constant electric field, as per this question, is a uniform field. Then field strength is not decreasing, so the spacing should be the same. Wherever you go, electric field strength is the same. That is the property of a uniform field, right? Yes, so that is why equal spacing. Fine, if we look at the last question, can electric field exist tangent to an equipotential surface? This conceptual question, we revised it many times. It cannot, right? What is the direction? I already mentioned during the discussion. Electric field should always be normal to an equipotential surface, right? Yes, it is always to be normal. Because if it is not normal, work done to move a charge will not be zero. Work done to move a charge from on an equipotential surface from one point to the other is zero. That is another property of equipotential surface. We mentioned many properties also during the discussion. Yes. So it should be normal. It cannot be tangential. It should be normal. Okay. So that work done to move a charge is zero. That's the reason. Okay. So as I told you, equipotential surface. Okay. Mark that particular topic. Yes. Moving on to the next. The electric potential as a function of distance x is shown in the graph. Yes. Yes, Venkata. Yeah. You have given the correct answer. How do we write that answer? So that's what I told you. This answer should be here. It cannot be tangential because if it is tangential, work done to move a charge from one point to the other on an equipotential surface will not be zero. It is actually zero, right? For that, electric field should be normal. If electric field is tangential, see, we explained that in the class, like, how it is not zero. Okay, we are not going for that anyway. It should be normal so that work done is zero. If it is not normal, work done will not be zero. Work done is supposed to be zero actually. Yes, that is the answer. Fine. The electric potential as a function of x. See, we are given a graph. Look at the graph. Variation of potential with respect to distance is given. Okay, variation of electric potential with respect to distance. You're asked to draw a graph, yes, showing the electric field as a function of x. How electric field is varying in this region, that is what we have to represent in a graph. Look at that. And concept, anybody? Yeah, based on? Exactly, electric field is equal to, E is equal to minus dV by dx. Yes, I'm getting so many answers then. Zabir, yeah, E is equal to, right? Electric field is the negative gradient of potential. That's a concept. This question is related to that concept only. See, look at this. In this case, negative gradient of this graph. Gradient of this graph is nothing but the slope, right? dV by dx. dV by dx is nothing but the slope of the graph. Slope of the graph is given here. See, this is the slope. And the same slope here also. See, but negative. So, if gradient, slope is a constant. We know E is going to be minus dV by dx, which is slope of the graph, which is a constant. In what range? In which region? 0 to 1, right? From 0 to 1 interval, E remains a constant because slope of the graph is a constant. It's a straight line with constant slope from 0 to 1. Got it? So this is nothing but slope. Slope is a constant. So electric field is supposed to be constant from 0 to 1. Now, check the next interval, 1 to 2. From 1 to 2, what happens? From 1 to 2, we can say electric field is going to be what? See, what is the slope of the graph between 1 and 2? Anybody? I mean, slope of the graph between 1 and 2. It is a straight line. It is a straight line parallel to x-axis, right? So slope is going to be 0. Yes, exactly. Yes, Smriti, Ashmita. Yeah, many of you are answering. So E is the slope, but slope is 0 here. So remember, when you draw the graph from between 1 and 2, from 1 to 2, there should not be an electric field. It should be 0. And when we come to the next part, see, the interval 2 to 3, we have the same slope, same slope, but negative. Same slope, but negative slope. Correct? And electric field is going to be a constant. It will be a constant, but like slope is negative. So now how to draw this graph? See, when you represent this graph, I'll just draw it here. Hope you can see. See, I'm going to mark this interval 0 to 1, then 2, then 3. Correct? We know from 0 to 1, we have a constant electric field. It is negative gradient of potential. So negative of the slope, right? dV by dx is the slope. So negative of the slope. So your electric field is going to be negative. See, minus dV by dx. Electric field is what? Minus dV by dx. So it comes below x-axis, right? And it is a constant. There is no change. It is a constant. From 1 to 2, what about the electric field? From 1 to 2. 1 to 2, we know electric field is 0. We already identified. So that is the way how we can represent. It is electric field variation. This is E and electric field is 0 on this line. And what about 2 to 3? Same slope but negative. So minus dV by dx. dV by dx is already negative here. So negative into this negative, it becomes positive. So this is how we have to complete the graph. Okay, so electric field is negative gradient of potential. A graphical representation is given. Yes. A good question, right? Yes. So nothing to calculate. We just have to know what is the relation between potential and electric field in a varying potential. Good. Okay, hope it is clear. Yes. No, Venkata, that should be just the other way around. Okay, first negative, then 0, then positive. I hope you got it. Okay, this comment is a little while ago. Fine. 4 point charges given in the next question. Capital Q. Yes, Smriti. 4 point charges. Capital Q, small q, capital Q again. One more small q. Look at the diagram. Are placed at the corners of a square of side A shown in the figure. Find resultant electric force on a charge. See, electrostatic 1 is coming up. Yes, we already completed. Anyway, potential energy of the system. That is what we are looking for, right? I told you potential of a system of charges and potential energy of a system of charges. Both of those topics, when we analyzed the chapter, we marked as important. Yes. Okay. So this is a question coming from that part. See, you're asked to find that total force. I hope you're okay with that concept. Still, we'll just running through it. I'm not solving it properly. This Q, right? Here we have to find out what is the total force. We know there are 3 forces acting on it. Other 3 charges will exert a force. Let us mark those forces. This is one of the forces, repulsive force acting on that charge because of this Q. Let me take it as F1. And there will be another force from this small q, that is also repulsive, that is F2, correct? And one more force exerted by the capital Q, and that one I am going to mark along this, right? Yes. So that is F3, F3. So we have to find out the total force, but there are 3 forces, right? We know forces are vector quantities. We can simplify 2 vectors at a time. We know the equation A is resultant is equal to root of A square plus B square plus 2AB cos theta. But for that we have only A and B. Here we have 3 forces simultaneously. You know what to do when we get 3 forces, right? Yes. So 3 forces acting on this charge cannot be simplified altogether. So what will we do? We will take first 2 forces, F1 and F2. See, so resultant of F1 and F2 is going to be F12 root of F1 square plus F2 square plus 2F1 F2 cos theta. This is the equation, right? Okay, but we know F1 and F2 are mutually perpendicular to each other. So this angle, yes, vector sometimes, then that is what we have to do because forces are vectors, of course. And this term is going to be 0 because cos theta is 0. Angle is 90 degree between F1 and F2. Okay, we considered only F1 and F2 at a time because we can take only 2 forces. Right, then you can find out F12 resultant. I am not going to solve it because this already we have done some sample questions before from this chapter. So root of F1 square plus F2 square will give you some resultant. And if you calculate this, you can see F1 and F2 will be of equal magnitude because same distances, same charges. Okay, so root 2 times of any one of those force will be the resultant of F12. But what we'll do after that? See, that resultant, we know resultant of F1 and F2 will be a bisector of this. So resultant F12 will be along the direction of F3, correct? Yes, and how will you calculate F3? F3 is K into Q, this Q divided by root 2 times A, right? This distance will be root 2A. If one of the side is A, this diagonal will be root 2A. Yes, we have done this kind of questions. So that is why I'm not going for in detail calculation. Fine. So we have F12 and F3 in the same direction. So finally, total force Fr is going to be F3 plus F12. The resultant of F1 and F2, F12 is added to F3 because they are in the same direction. You will get the total force here. We don't have any numerical values given, so it will be some equation form. Okay, right. So that you try, we know how to proceed. Okay, so since it is from the other chapter, we are not going to spend time on it. Now, the second part, look at the B question. Potential energy of the system. Okay, so one question is from electrostatics chapter 1 and the second sub question is coming from chapter 2, right? Fine. So how will you calculate potential energy of a system? What was the equation? We know for a pair of charges, if you have two charges, potential energy equation Q1 and Q2 separated by a distance r, U is equal to K Q1 Q2 by r squared, correct? That is what we have to do for a given pair of charges, two charges. And if you have more charges, more than two, what did we do? We identified, yes, Salman, okay, Zabi, I'm seeing your answer, okay, keep going, okay, keep solving along with me. K Q1 Q2 by r square, that is the equation for two charges. When we have more than two charges, what did we do? We considered the possible independent pair of charges, correct? How many independent pair of charges possible in this case? See, this is charge 1 and this is charge 2, charge 3 and charge 4 suppose. 4 charges are given. 1 and 2 is one possible combination, one pair. 2 and 3, second pair. 3 and 4, yes, how many pairs? Come on. 3 and 4 is the third pair. 4 and 1 is the next fourth pair. Correct? And we have two more pairs, yes, which are they? Diagonally, 1 and 3 and 2 and 4. So there will be total 6 pair of independent pairs of charges in this combination. And we will apply this equation for those 6 independent pairs. That is your final answer. And take the sum of them, that's it, right? We will take all of these individual pairs. Total sum of potential energy will be the total potential energy of the system. That is how we calculated, right? Yes, yeah, 6 pairs, yes, Salman. And that is what we explained. Now we will go for that. See, U is equal to, first pair I am going for Q and small q. So we have K into capital Q and small q, correct? Look at the next one, capital Q, small q again, plus K, Q, Q, plus look at the next pair, capital Q, small q again, K, capital Q, small q. The last pair, fourth pair is also same, K, Q, Q, right? Plus the next two pairs, you can see capital Q and capital Q. So K into capital Q square divided by root 2 times A. Wait, we forgot to divide by distance, right? This is divided by A. These are all divided by A. Yes. Correct? Yeah. And we get the next pair, fifth pair is this one, Q, Q. And the sixth pair is small q combination, K small q square divided by root 2A. We know this distance is going to be root 2A. We already mentioned that before, root 2A. So the first 4 pairs, you can take the sum of them. See, U is equal to 1, 2, 3, 4. So 4 into K, capital Q, small q divided by A, plus, look at this, we have 2 times K divided by root 2A into Q square plus Q square. Because we have common terms, right? That is why we have taken out. So we can say 2K by A can be taken out, 2K divided by A. So 2K by A is gone. So 2 into capital Q into small q, correct? Plus, we can say 1 by root 2 here, plus capital Q square plus Q square, right? Actually, this is all together, one single term. So plus capital Q square plus small q square, the whole divided by root 2. You cannot simplify further because we don't have any numerical values given. So that is the equation. That equation is the final answer. Okay. So the point is, we will consider all independent pair of charge, charges possible. 1 and 2, 2 and 3, 3 and 4, 4 and 5, 4 and 1. Then 1, 3, 2, 4. Total 6 pairs, 6 different terms we added up. Okay. Exactly. Yes, Shahzar. That is what we have done. Good. Come on. Let's move on to the next. We're coming to the capacitance. Okay. So remember, potential due to a system of charges, potential energy due to a system of charges. You know, these two concepts, as I told you, just make perfect. And here in this question, we have given a capacitor. Okay. And that slabs are filled, you know, the space between the slabs is filled with two different dielectric materials, as you can see in the diagram. 2K at a distance, it is not equally divided. For d by 3 distance, we divided, you know, we filled that with one dielectric material, and the remaining distance 2d by 3, we filled that with another dielectric material of constant K. You are asked to find expression for capacitance of this particular system. What is the capacitance expression for this combination? That is the question, right? Okay, let's see. We have done this kind of questions before, but at that time it was equally divided. It's a small change in this case, like, you know, it is not half, like divided equally. First part is d by 3, second part is 2d by 3. Whenever you get capacitors arranged side by side, end-to-end connection, you have to consider those capacitors as a combination of, what combination? Series combination of two capacitors, right? Yes, series combination of two capacitors. So we can say this capacitor has an equivalent capacitance C equivalent, which will be a combination of capacitance of capacitor 1, C1, let me take the small one as C1, and the broad one has C2 capacitance, and combination of C1 and C2 in series is the equivalent capacitance, correct? Okay, we know how to calculate equivalent capacitance in series combination, right? 1 by C equivalent is equal to, yes, 1 by C equivalent is equal to 1 by C1 plus 1 by C2. We just substitute those values here and simplify. We will end up with the correct answer within 2-3 steps. Okay, so let us identify what is expression for C1 first. What is your C1? C1 is a capacitor which has a plate separation d by 3, okay, d by 3, and plate area A. See, plate area is A only for both of the capacitors, but separation between this, the plates is different. For the first one is d by 3, and it is filled with a dielectric material of QK, 2K constant. So we can say epsilon 0 A divided by D is the expression for capacitance of a parallel plate capacitor, right? This equation is important. Its derivation is also important, right? Then we have to multiply with the dielectric constant, which is 2K, right? 2K. Only for C1 we are doing now, okay? For 2K. And what about the plate separation? It is not D, it is D by 3. So actually we can just rearrange this. 3 comes up. So 2 into 3 becomes 6K. 6K epsilon 0 A divided by D. Good. C1 is ready. Now what about C2? In the same way we can find out C2 also. C2 can be again epsilon 0 A divided by D equation. What is the constant? Dielectric constant this time? K. So we have to multiply with K, and plate separation is not D, it is 2D by 3. So we have to substitute 2D by 3 here. Correct? 2D by 3. So 3 comes up here also. We can say 3K epsilon 0 A divided by 2D, right? This is your C2. Now if you substitute C1 and C2 in this equation, very easily we can solve this. We will find the final answer. So let us try. We can say 1 by C1 is what? 1 by C1 is reciprocal of this value, right? So we can say D divided by what? 6K epsilon 0 A plus, what is the second one? 2D divided by 3K epsilon 0 A. So 2D divided by 3K epsilon 0 A. Yes, so we can simplify this. We can take 6K epsilon 0 A as the LCM, right? So here it is just D plus, see this is only 3K epsilon 0. We have to multiply with the 2 here. So we get 4D. Yeah, 4D plus D is going to be 5D divided by 6K epsilon 0 A. Remember, don't stop your solution here. This is only 1 by C equivalent. One of the most repeating mistake here. LHS is 1 by C equivalent only, correct? You have to find out C equivalent. If it is an MCQ question, they will give both options, okay? One option will be this, one will be reciprocal. So remember, LHS is 1 by C equivalent only. Therefore, C equivalent of this capacitor is going to be just the reciprocal. We have 6 by 5 into K times epsilon 0 A divided by D. See, this is the final answer. So that question was, that diagram was a little scary maybe. Yes, but very easily we solved it. We considered these kind of capacitors always, they are connected end to end, like, they are series combination. And we had similar kind of questions when they are filled the other way around, right? So instead of like this half and this half the other way, we tried these kind of questions before. That was parallel combination. And end to end connection is going to be series combination. Good. So that is the final answer. Yes. People are doing. So we are getting so many answers. Very good. Next one. And this is capacitance. Once again, you can see a diagram. Most of us has this problem whenever we see these kind of networks. It's a little scary, right? Let's see. In the following arrangement of capacitors, the energy stored in 6 microfarad capacitor is E. These people are not giving us the numerical values. So we have to play with these variables. E is the energy in which capacitor? In 6 microfarad capacitor. Okay, fine. Then the question is, find the energy stored in 12 microfarad capacitor. What is energy in this one is to be calculated. And you can see from the diagram, 6 and 12 are like, parallel to each other. Followed by one more capacitor is there. Obviously, next question is for energy stored in the 3 microfarad capacitor only. Fine. Then fourth and third question is to find what is the total energy drawn from the battery. We can say if I take this as E1 and this as E2, and if this is energy E3, we can predict our answer. Finally, for third one, total energy is going to be equal to E1 plus E2 plus E3. So the third question we don't have to solve. Like, if you solve it question number 1 and 2, you can get what is E2 and E3. E1 is already given as E, right? So you'll get the final answer there easily. So we have to find what is the energy stored in the second capacitor, like, this one. That is a task, right? Then later we have to find out E3 also, right? Then we'll take all the sum of them. Okay, now let's see. Question says that energy stored in the 6 microfarad capacitor is E. So how can you find out energy stored in this capacitor? We have equation Q is equal to half CV square, right? I'm going to take half CV square. We have other formats like half QV and Q square by 2Z, different forms. I prefer CV square, half CV square, because these two are in parallel combination. So they have same potential, right? Same potential. So let's go for like capacitor 1. So this is my C1, right? For C1, energy E1 is equal to, how will you calculate? Half C into V square. Half C V square is going to be half into, we know the capacitance 3 into 10 raised to minus 6, but we don't know what is V. We don't want V, let us keep it as it is, okay? Half C V square. So this is your E1, and question says that is E. Energy in the 6 microfarad capacitor is given as E. Yes, so we can say E is equal to, what is E? Half into 3 into 10 raised to minus 6 into V square. Okay, let it be there. Let it be there. Now, what will be energy stored in the second capacitor? That is the first question, right? Energy in 12 microfarad. See, I told you already they are in parallel combination, so potential is going to be the same. In the sixth, like energy of the second capacitor, E2 can be half into that capacitor into V square, right? V is the same for both. I mean, for 6 microfarad and 12 microfarad. So half C2 V square. Half into C2 is going to be 12 into 10 raised to minus 6 into V square. Got it? Yes. See, we can say this will be half into, like, C2 is going to be 12 into 10 raised to minus 6 into V square. Yes. So we get 12 into 10 raised to minus 6 into V square. That is energy stored in the second capacitor, right? And if you compare this, we can say this E2 is going to be, if you take the ratio, E1 and E2, if you take the ratio, we have half 10 raised to minus 6 and V square. 12 by 3 is going to be what? Just 4. So E2 is going to be 4 times E. right? Yes. So this is what we got. Like if E is the energy stored in the 6 microfarad capacitor, then energy in the second capacitor is going to be 4 times E. Correct? Fine. Then we don't know the value of E, so we keep the answer in E only. What about energy stored in the next capacitor, 3 microfarad capacitor? In 3 microfarad capacitor, we can say it is not easy because potential is not the same there, right? Potential is not the same. But for, we know, if they are connected in series, not the potential, but charge is going to be the same. Q is a constant. So I can say a total charge stored in the combination of 6 microfarad and 12 microfarad is equal to charge in 3 microfarad capacitor. Correct? So they are in series combination, charge remains the same. Yes. See, we have a small problem here. We have taken instead capacitance is not 3. Capacitance is, we calculated capacitance 6 microfarad. Good. So it's going to be 6 into 10 raised to minus 6. Instead of that, I wrote 3 microfarad. Okay? No. We have to take 6 microfarad. So 6 is going to be here. Sorry for that. Instead of 3, instead of 6, we wrote 3 here. So I changed that. So this was E. This was E. Now look at this. If that is E, this will be 2 times of that quantity. E2 is going to be 2 times E1. Right. Yeah. So make sure that value be Ashmita Chakravarti, right? Thank you for reminding me that substitution was wrong. Good. Very good. Very good. So instead of 6, we substituted 3 microfarad. That was the correction I made. Fine. So first part is over. Like energy in the second capacitor, in the 12th microfarad capacitor, we calculated. Now when we come to the third one, like 3 microfarad capacitor, what to do? I told you charge remains the same. How will you calculate charge in a capacitor? Q is going to be equal to C into V. So total charge of this combination, parallel combination, we can say Q1 plus Q2. So 6 microfarad 10 raised to minus 12 into 12 into 10 raised to minus 12, sorry, plus we add them up, parallel combination resultant is the sum of the two, into V. C into V can be equated to charge in this capacitor, which is 3 into 10 raised to minus 6 into what? Maybe V dash or something. Okay, potential is different. We don't know. We have to find out that potential, then only we can find out the energy finally, half CV square. So this will be 18 into 10 raised to wait. Power is 10 raised to minus 6, right? Plus 12 into 10 raised to minus 6. So we get 18 into 10 raised to minus 6 microfarad into V equals to 3 into 10 raised to minus 6 into V dash. So we can cancel 10 raised to minus 6 from either side. We can say V dash is going to be 3 and 18 can be cancelled by 6. So we can say V dash is 6V, which means potential drop across this capacitor is 6 times V, where V is the potential difference between the other two capacitors, 6 microfarad and 12 microfarad. And now it is easy. If you know the potential difference, we can go for the equation energy is equal to half CV square. And that will be, yes, V dash is 6V, X times V. That is the correct answer, but that is not your final answer. We have to find out energy of that capacitor also, right? Very good. So let us calculate. I want to change the screen. See, what will be the capacitance now? Capacitance of the third capacitor, energy in the third capacitor, E3 is going to be equal to half C into V dash square. What is V dash actually? V dash is the 6V that we already calculated. Now substitute. We get the value here, half into 3 into 10 raised to minus 6 into 6V the whole square. Okay, 6V the whole square. So we get half into 3 into 10 raised to minus 6 into 36V square. Correct? Fine. So what is this value? Half into 3 into 10 raised to minus 6 into V square value we know already into 36, right? That is E3. Correct? Okay. V dash we substitute properly, no? Yes, that is 6V. So we get 36 V square. Now what was our E value? E is half into 6 into 10 raised to minus 6 V square. It is given that E is equal to half into 6 into 10 raised to minus 6 into V square. Okay? Yes. So if you write this as, half into 3 into 10 raised to minus 6 into V square into 2 into 18. See, I am splitting 36 into 2 into 18 so that this can be E, correct? That is the value of E given in the question. So finally, we can say E3, the third energy is going to be 18E. That is energy stored in the third capacitor. Okay, see that substitution, be careful. We had energy value given as E, a variable, it is not any numerical value given. That E value we defined right in the beginning as half into 6 into 10 raised to minus 6 V square. That value we compared with the new energy and we found it is 2 times of this value. So we wrote energy in the second capacitor, energy in that 12 microfarad capacitor was like 2E, right? If this is E, this is 2E. Now we calculated this capacitance value. For that, first of all, we found out what is the potential across that capacitor based on the concept that series combination Q remains the same. So we identified that charge in both the capacitors from which we found out V dash, which is actually potential across this capacitor. So that half CV square can be used to find out the energy finally. Yes, that is what we did. And in that E3 also we compared with E. This was the E value. And what excess we got? 18. So E3 is going to be 18 times E. Yes, so we finished our calculation part. Now the last one is total energy. I told you, if you already solved first and second question, second part, third part is not an issue. It is a sum of all energy, E1, E2 and E3, correct? So we already have E. For this capacitor we have energy E. For this one we have 2E. And for this capacitor we have 18E as per the calculation. So what is the total energy? In the third part of the question, we can say total energy is going to be, total energy will be E plus 2E plus 18E. We have 21E is our final answer. Yes, exactly. Yes, Ashmita. Yes, many of you saw. Smriti, Venkata. It is 21E. Yes, exactly. That is of total answer. And that's what I told you. If you're okay with the first two calculations, third one is not an issue. It is just the sum of all those energy parts. Okay? Yes. Good. Fine. So let us move on to the next. When we get, capacitors combination, be careful about the substitution and identifying the combination also. Don't be confused. Be careful. Fine. Moving on to the next. I think that is the end of that short answer questions. Now we have to mention those long answer questions also from the chapter. As I told you before, all the derivations related to dipole, they are going to be very, very important. Even from the first chapter, we have electric field on axial line, equatorial line, torque, potential energy. Now from this part, derive expression for electric potential due to a dipole. That is one of the most repeating 3-mark question from this chapter. Make sure you revise this derivation properly. Okay. Anyway, we are not going to waste time on that particular question. Another one, find expression for potential energy of a system of charges. See, in that analysis I told you, one of the hot topic of the chapter is potential energy due to a system of charges, right? So that also asked for 3 marks before, and it's a part of 5 mark also. So make sure you're revising it properly. Potential energy of electric dipole once again, see, and you're asked to explain stable and unstable equilibrium of that particular concept. Right, fine. So I think that is the end of that potential and capacitance part. I think we can continue with moving charges, right? Sorry, current electricity is also in between. So we will start with current electricity questions. Sir?
Ready.
Yes.
Yes, once again, good evening. So thank you for your active participation. Like this session, we don't know till what time it will be extending. Anyway, we are trying to wind it up quickly. But this active participation, you have to maintain the same tempo till the end. I told you, like at the end, we'll be discussing some graphical questions, analysis, circuit analysis question and all. So be online. Thank you. So we are going to start current electricity. You know the importance of this chapter again, like the chapter with lot of weightage. So look at this. Look at the analysis for the last 10-year papers. Like I think I'm audible to all of you. Please comment. Everything is fine, no? Yeah. So let's check what are the areas like electric currents in conductors, Ohm's law, drift velocity, limitations of Ohm's. Look at the third part of this chart. What is that? It is from drift velocity. Drift velocity part, that is a very, very important topic in this chapter. So all of you should study the derivation, all the formulas related to drift velocity carefully. Then there is resistivity of various material, limitations of Ohm's law, small question they can ask. Sixth one, look at that. There is total 6 mark question came from that. That is from temperature dependence of resistivity. That is mainly the graph thing. So you have to go through the graph. I'll tell you it in detail. Then 7th one is electrical energy power. Then 8th one again you can see like 8th one EMF cells internal resistance. So that part is also very important. And then Kirchhoff's rules, obviously. Kirchhoff's rule questions will be there, numerical type. Cells in series parallel, and finally Wheatstone's bridge. So this is, I think you got an idea about the important topic, isn't it? Yeah. So let's go to the questions now without wasting time. Look at the first question. Question is based on drift velocity. Define drift velocity of electrons. So that is a direct question. Define what is the meaning of what is drift velocity? Average velocity acquired by free electrons subjected to an electric field is called the drift velocity. Drift velocity of electrons are conductor connected across a battery. Figure shows the variation of the drift velocity of electrons in two copper wires A and B of different lengths versus the potential difference V applied across their ends. So look at the graph. This graph is between drift velocity and what? Potential applied across two copper wires. Two copper wires of different length. Length is different. Okay. Then first question is, what does the slope of the line represent? So what is the physical significance of the slope of this line? That's the first question. So this chapter you can see lot of graph based questions you can see. So don't miss it. So read it carefully. You can easily answer it. So what is the first question? Graph. So here you can see drift velocity. Here what is it? Potential. So slope means it is, it is slope is y by x. So what is y? Along y axis you can see drift velocity. Along x axis potential is there. So slope means y by x means drift velocity by potential. Let's see what does it represent. So tell me the formula for drift velocity. What are the equations? Drift velocity, the one formula which we derived is E is equal to the magnitude E by m into tau. Hope you remember there is a negative sign. So that sign is not important for this case anyway. Vd is equal to minus E by m into tau. E, charge of electron, capital E, strength of electric field, and m, mass of electron, tau, relaxation time. Yes or no? Right. Now, here you can see we need a relation between drift velocity and potential. Potential, here this is field. Tell me what is the relation between field and potential? You know that E is equal to V by D, but here I am taking S, the distance as L, length as L. So we get V by L. So we can write it as E by M into V by L into what? Tau. Then what we need? Slope indicate. You can see from the graph, slope will give you Vd by V. Alright. So slope is equal to Vd by V. This is a slope. So they are asking what does slope indicate. You can see slope with the remaining terms only. That is E by M tau by what? L. This is what the slope of that graph will give you. Slope will give you this quantity. Okay. Slope will give you this one. Is it clear? Yes. Very good. Venkata, VPS Thug Life. Okay. Right. Now, there is... So first question is easy. We got an idea. What does the slope of the line represent? Now, which one of the two wires is longer? Can you answer this question? Now it's easy because look at the slope. How the slope and length is related. You can see that the slope is, where is L? L is here. So the slope is inversely proportional to the length. So the one with less slope will have what? More length. So what is the answer for that? Smriti, right answer. Nachiappan, right answer. Yes. Mahek, very good. The wire B will be longer because it has less slope. I hope this is very clear. Before going to the next question, once again, drift velocity, mobility. What is mobility? Drift velocity per unit electric field. And is there any other formula for drift velocity? There is a formula, actually it is a formula for current. There may be questions based on this as well. We know that current I is equal to NEAVD. You remember this? Yes. What is N? N is the charge density, number density of electrons, number of electrons per unit volume. E is charge, A is the area of cross section, VD is the drift velocity. So based on the question only you need to pick the formula. Alright. So can I go to the next? Yeah. Going to the next question number 18. 18, we need to, as I told you, we need to cover 50 questions today, 50 important questions and related concepts. So listen carefully. Your mind is very important. You have to focus. Okay, you have to think. When a question is displayed, your mind should work properly, your brain should work properly. Surely that is going to help you for the exam. So define the term drift velocity and relaxation time. You know that. What is relaxation time definition? The time interval between two successive collisions. Okay, now look at this. A conductor of length L is connected across a source of EMF E. If the conductor is replaced by another of the same material and area of cross section but of length 5L, by what factor will the drift velocity change? So it is question related to the previous formula only. Question related to the previous formula. There is a doubt, sir. Can you please show field lines for a point positive charge kept inside a spherical conducting shell at a position that it is not at the center? King Pepper Bowl. Okay, can you tell me your name? I can see King Pepper Bowl. Alright, so your doubt is like if a charge is kept inside a, can you please show field lines for a positive charge kept inside a shell? Okay, so there is a shell and the positive charge is kept. Okay, positive charge is kept over here, not at the center, right? Okay, so over here. Then what is the direction of the field lines? That's your doubt. Yes or no? BPS thug life. Okay, like so here what you have, you know that the static induction will be taking place, negative charge will be induced on the inner side and the field will be lines will be from positive to negative. So there was a doubt. Let me explain that doubt first and after that we'll come back to this question. So since it is close to this side, more charge concentration will be here. So it won't be like if it is exactly at the center, the lines will be radially outward like from positive, but it's close to here means it will be something like more lines will come here and then it will be going in this way. Okay, and you can draw it outside as well. I hope it is clear. Anis, is it okay? Yeah. Yeah, thank you. Can I go to the next? Listen here. So a conductor of length L. So initially the length is L, then it is 5L. So what factor the drift velocity change? Anybody got the answer? So let's go back to the previous question. How drift velocity related to L? It is inversely, so you can see inversely proportional to L. So drift velocity is inversely proportional to L. Okay, then the second case it is 5L. So VD dash will be proportional to 1 by 5L. Inversely proportional. So VD dash by VD will be equal to what? Inversely proportional means we can write it as L by 5L. So what is the answer? VD dash is equal to VD by 5. So by what factor? What is the answer? Very good. That's Ansh. CID Samosa. Right? Nice name. Okay. 1 by 5 is the right answer. S decreases by 5. Mahik. Okay. Right. So I hope it is clear. So please concentrate on drift velocity. I've already shown you like how many questions came from that. The priority of asking questions from that topic is very, very high. Let me go to the next question number 19. Graphs. So 3 graph questions together you can see here. First one is plot a graph showing the variation of resistivity of a conductor with temperature. 2015 question. Okay. Show the variation of resistivity of copper as a function of temperature in a graph. 2014. Copper is a conductor. Like, do you remember? Please, those who have confusion, open your reader textbook in current electricity chapter. You can see many graphs. These two, the conductor and resistivity of a conductor with temperature. So you can start from 0 Kelvin, 50, 100. So here you can put resistivity. And do you remember the shape of the graph? It is something like this. Yes or no? You know that the resistivity is directly proportional to temperature but not exactly the straight line. Alright? Yes. Clear no? Fine. So this is a graph that will be same for copper as well. Copper as well. The same shape will come. Then look at the third one, plot a graph showing variation of current versus voltage for the material gallium arsenide semiconductor. Okay, that also you can see a clear graph in your reader, like I is here, voltage is here, the shape of the graph gallium arsenide. Hope you remember the topic, failures of Ohm's law. So semiconductors does not obey Ohm's law. You know that gallium arsenide is showing like the value of V and I is not unique. You can see there are two different values of I. Yes or no? Two different values of V for the same value of current. Alright, so it's a pure example where you can say the Ohm's law is not valid. Is it okay, these graphs? So please go through that. Those who have doubt, is Venkata Smriti. Very good. Yes. Question number 20. Yeah. Look at this. It's an important question. The plot of the variation of potential differences across a combination of three identical cells in series versus current is shown in the figure. What is the EMF and internal resistance of each cell? EMF and internal resistance of each cell. So how many cells are there? Combination of three identical cells. Combination of cells. Quickly recall the formulas and concepts. Derivation may come for combination of cells in series and parallel. So tell me, what is the formula for net EMF when cells are connected in series? You know that it is E1 plus E2. EMF can be added up. Okay, identical cell means the situation will be very easy. It will be E plus E plus E plus. How many cells are there? That many times EMF of one cell. So here you can see there are three cells, each of EMF E we can take. So we get 3E as a total EMF. And what about parallel combination? Do you remember in parallel combination what is the formula? E1 R2 plus E2 R1 by R1 plus R2. What are R1 and R2? Internal resistance. Internal resistance. Okay. So here this is a series combination. So this graph is between what? Variation of potential differences across a combination of three identical cells. What is the EMF and internal resistance of each cell? So here we can write net EMF. Three identical cells are connected in series, means if EMF of each cell is E, three cells will be what? 3E. And in the same way, if three cells, if you are connecting like this, look at this, this is first one, it will be having an internal resistance R, second cell, internal resistance R, third cell will also have an internal resistance R. So this is E. See, we already got E net is equal to 3E. Similarly, what will be the net internal resistance? R net will be equal to what? 3R. Now this graph is between terminal potential difference and what? Current. So what is the equation for terminal potential difference? V is equal to E minus IR. You know, this is the formula for terminal PD. I hope all of you remember this equation. Terminal potential difference is equal to E minus IR. But here what you have to write? We need to write E net because it's a combination of cells. E net and I what? R net. Okay, so E net value, you know that it is how much? 3E minus I into R net is what? 3R V. So what we have to find? We need to find internal resistance and EMF both. So that now it's very easy. You can just check the graph. At this point, what you can see, I is equal to 0. It's on x-axis. At the origin, you know, current is taken along x-axis. So at that, over here, at this point you can see, it is on the y-axis, means x coordinate is 0. So over there, what is the voltage? 6. So if terminal PD is 6 volt, current is equal to 0. So that value you can substitute here, then you will get the answer. Voltage is 6. 3E, at that time what is the current? Current is 0, so I is equal to 0, so this term will become 0. So what is E? E is equal to 6 by 3, which is equal to 2 volt. 2 volt, simple. Yes or no? Yes, right. Now what is the other thing? They are asking what is the internal resistance. For that you can consider the other point, this point, other point. On that point you can see V is equal to 0, but I is how many ampere? It is given as 1 ampere. So that you can substitute in the same formula. In the same equation I am going to take V as 0, so I get it is 3E minus I is 1 ampere, I into what? 3R. So what I get? I'll get 3R is equal to 3E. We need R. Okay. So R is equal to what? E, right? So E is 2. So we get 2. Clear or not? Please comment. Is it okay? Yes, Ashmita, others also. Please comment. Then only you'll understand. You people are listening. Your response is very important. Yes, Smriti, very good. Thank you very much. Let me go to the next question. Question number 21. A cell of EMF E and internal resistance R is connected across a variable resistor R. Plot a graph showing the variation of terminal voltage V of the cell versus current I. Using the plot, show how the EMF of the cell and its internal resistance can be determined. Look at this question. This is a 2014 question. Okay. So listen please. A cell of EMF E. So there is a cell of EMF E and having an internal resistance R. So this is E, this is R. It is connected to what? An external resistance, variable external resistance R. So they are asking, we need to draw a graph between V and what? I. You can see in the previous question, it is a graph between V and I. Let's see whether we are getting the same graph only in all cases. So for that, let me just write the equation for terminal PD. What is it? V is equal to E minus IR. E minus IR. Okay, so we need a graph between V and I means you can see that our y-axis, the y coordinate has to be V. V should be along which axis? Y-axis, and along x-axis we need what? I. So if I'm making a small rearrangement, look at this students, V is equal to E minus IR. You know that EMF is a constant. So can I write it like this? Minus IR plus E. That means V is equal to, look at that, minus R into I plus E. I did not add any new term, just rearranging. So what is the purpose of writing like this? You can see that this is exactly an equation of what? A straight line. Y is equal to mx plus c. Isn't it? Yes. So from that, what you can see, this is a straight line, but look at m. M is slope of the line, that is minus R. That means slope is negative. So the graph will be a straight line with a negative slope. That means the shape of the graph will be like this. This is what we got in the previous question. In the previous question, this was a question. So you can see the graph is like this. Is it okay or not? Please comment. Now they are asking how can you determine what internal resistance? Internal resistance is slope of the graph only. Slope of the graph only will give you what? Internal resistance. EMF, how can we find? So you can take V is equal to 0. The y-interception is what? EMF. C is Y. So y-interception, so at what point it is meeting on y-axis, that will give you what? EMF. So don't skip this type of question and don't draw a simple graph like current electricity. There are many graphs, so don't make any guess, like you can easily find this. It is not a tough question. So y-interception will give you the EMF and slope will give you the internal resistance. Okay or not? Yes. Alright, so 21 question has been completed. Now 22, Sunil sir, I think.
Can I join?
Yeah, yes.
Okay, sir.
Thank you.
Thank you so much. Let's continue with question number 22. Again, this is a graph question. Just like GB sir mentioned, we have lots of graphs like in current electricity, and we will be just combining all those graphs together. As I told you right in the beginning, we have a special session on graph questions alone at the end of this discussion, and also devices. So stay tuned. We'll be just going through that. Okay. So look at this question. Again, a cell of EMF E and internal resistance R is connected across a variable load resistor R. See the same, it's a continuation of, like, it's a similar question like before. Draw the plots of terminal voltage V versus R and the current I. Yes, we have two different cases here. Second part, look at this question. V versus I graph we just solved in the previous question, right? So that part is okay, I hope. JB sir explained that question well. Now what we have to do here is, since it's a combination of both, we'll just go for this part, okay? Because the other one already we discussed. Okay, then we have a sub question also. So first let us complete the graph, the variation of V versus variable external load resistance. This graph is slightly confusing. So look at this. We know expression for terminal potential difference of a cell V equals to E minus I into R. Just like you used in the previous question, same equation. So we have to draw a graph V and R. Relation between V and R is to be found out. External resistance R. And when we come to that, we first of all we have to get an expression for an equation which connect both capital R and small r. Correct? Yes. So we have V is equal to I into R, right? Terminal potential difference of a given cell is going to be R is the external resistance, the load resistance. The question talk about load resistance, that is capital R. I is the current flowing through the cell. So these are the two equations we know. Okay, so we have to go for this V and R relation. We cannot say it is directly proportional because that is related to current also. So how will you calculate current in a given circuit, like a cell of EMF E and a terminal potential difference V or internal resistance R? See that also given in the question. External resistance capital R. Total current in that circuit is going to be EMF divided by total resistance R plus R. Correct? Current is equal to E by R plus R. So let me take the second equation. See this equation to identify relation between V and R. That is the first step to draw the graph, right? If you want to understand what is the shape of the graph, we have to get a relation connecting them. Now look at the second question. Let me substitute for I. I is going to be EMF into resistance divided by capital R plus R. Okay, that is V. Now we can say V and R are related in that equation, but that's a complicated relation. We have an R in the numerator and R in the denominator also. So we cannot infer the exact relation from this equation, right? So let us modify this one. I'm going to take that R common in the denominator. See, R into 1 plus small r by capital R. Okay, so now you can cancel one of the R from this, We are just restricting that R only in the denominator so that we can infer the relation from that. So finally, we get V equals to EMF divided by what else? 1 plus small r divided by capital R. This is the equation we are going to refer to draw this graph, the first graph. V is equal to EMF by 1 plus R by R. Now we have a relation connecting this V, which is the terminal potential difference of the given cell, and R, which is the external resistance connected. So how do you understand this relation now? What happens when I increase this R? If I increase this R, actually the total denominator is decreasing, right? On increasing this R, what happens? The term R by R decreases. The term R by R decreases means the whole denominator is decreasing. What happened to the potential difference? It is on the LHS. It increases. When the denominator decreases, this value increases, right? So finally, we can conclude R and R. When you increase external resistance, this terminal potential difference also increases. This is what I told you. That relation is a little complicated, right? Yes. So the conclusion is when you increase R, this V also increases. You got it? But will it be a straight line then? Is it directly proportional? Not exactly. If it is directly proportional, V will be equal to R. That can some constant into R. That kind of equation we are supposed to get. But this is not directly related. Still on increasing R, V increases. And one more point you have to remember. If you increase R and R becomes infinite, for example. Okay. So at that time, current reduces to 0. Correct? If R is infinite, it's an open circuit, current reduces to 0. When current reduces to 0, we know for any given cell, terminal potential difference is equal to EMF. Maximum value of terminal potential difference can be EMF. It cannot exceed EMF. Now look at the graph. What are the things you know? 2 points. One, on increasing external resistance, terminal potential difference also should increase. Second one, maximum value of terminal potential difference should be what? EMF of the cell. Now let us represent in a graph. See, this graph is going to be like R versus terminal potential difference. Okay, see, maximum value of this terminal potential difference is going to be, that is said to be EMF of the cell. So we fixed that value. Now, as per the relation, as per this relation, what should be the way how V varies? I explained already. When R is increased, V also increases, but not as a straight line. It is not a linear relation. It's a curved graph. See, so on increasing R, E also increases. But will it increase forever? Will it increase forever? No. We have a limit for that, right? What is it? When R increases, when R is equal to infinity, when R is equal to infinity, current in the circuit reduces to 0. Whenever current in the circuit is 0, what about V? It is equal to E. So V has a limit. Its maximum value is E. That is why the graph ends when it touches this line. Got it? Yes. See, 2015 paper. That ratio, that particular graph is like a little confusing. That's what I told you, because we have to understand exact relation. Then only we have to draw the diagram. You got it? Is that clear? So I explained that graph in detail because we don't have to waste time on the second part that we already solved before. In the previous question, we shall explain that part. I hope it is clear, right? So this should be the graph, V versus R graph. V versus R graph. That is the first question, V versus R graph. Second question is V versus I graph, which you already have done in the previous question, this one. So these two graphs you're supposed to draw as an answer for the first part of the question. Yes, Venkata. Yes, Zabir. Yes, the same graph. See, the problem with this graph, as I told you, that concept is very important. How it can be affected, like, on increasing external resistance, how it affects the terminal potential difference. If you know that concept only, we can draw this graph. Okay, so just remember this graph whenever we get V versus R and V versus I. These are the two possible graphs from that cell part. Okay, V versus external resistance R, V versus I graph. We know both the graphs now. That part is solved. Okay, we learned. Good. Moving on to the next. Sorry, we have a second part of this question. Second part of the question says, it is found that when external resistance R is equal to 4 ohm, the current is 1 ampere, and when R is increased to 9 ohm, the current reduces to 0.5 ampere. So you are given a cell, we are going to change external resistance. When it was 4 ohm, current is 1 ampere. When it is 9 ohm, current is found to be 0.5 ampere. Using those values, we have to find out its internal resistance and EMF of the cell. Okay, so that part is quite easy. I'll show you what to do. It is given that when R is equal to, when R is equal to 4 ohm, current is 1 ampere. See, I'm just taking those values here so that you can refer for calculation. Another condition is given when R is given as 9 ohm, current in the circuit is 0.5 ampere. Using these two, we have to find out EMF and internal resistance. Let me cross check the values. 4 ohm and 1 ampere, 4 ohm and 1 ampere, 9 ohm and 0.5 ampere. Okay. Easy now. See, look at that. How will you calculate total current in the circuit? I is going to be EMF of the cell divided by R plus small r. Correct? R plus small r. This is the equation for total current in the cell. Right? Now, see, we don't know what is the EMF of the cell. That is to be calculated. We don't know what is even R also, small r. That is also to be calculated. So we have two variables. We need two equations. Simple. Those two equations help you to solve it. Look at this. In the first case, I am substituting R as 4. At that time, current is 1 ampere. So we can say 1 is equal to EMF we don't know, 4 plus R. Correct? Yes, 4 plus R. So we can say 4 plus R is going to be equal to E, equation number 1. Okay, we can form one more equation using the same. I is equal to E by R. So what was I in the second case? 0.5 ampere. When current is 0.5 ampere, EMF divided by, at that time capital R was 9 ohm. So we can say 9 plus small r. Got it? So when you take this, 9 plus R is equal to EMF divided by 0.5, or we can say this is 2 times EMF. Equation number 2, I'll write it here. 9 plus R is equal to 2 times EMF. Equation number 2. See? Easy. Now we know two equations. We can just subtract one from the other so that R gets cancelled. Small r gets cancelled. Anybody? Yes. Yes, Ashmita. Sir, yes. Yeah. Yeah, many of you are solving it. Keep going. So we can calculate by subtracting this equation number 2 minus equation number 1. 9 minus 4 is going to be 5. R reduces, they cancel each other. 2E minus E is going to be E. So EMF of this cell is 5 volt. We directly got the answer. One part of the answer is EMF. The second part is that internal resistance. So how will you find internal resistance? Take any of these two equations, you can find out that. Equation number 1 can be used. 4 plus R is equal to EMF. EMF we found as 5 volt. So R is going to be 5 minus 4, which is 1 ampere. Yes. So as a final answer, R is equal to 1 ohm and EMF is 5 volt. Okay. So we had two variables, we formed two equations. That's what we do. Okay. So see, a proper understanding of the cell concept is very important. Then only we can solve these kind of questions. Okay. And if you change one quantity, how it will affect the other. So make sure cell is a very important concept in like current electricity part. Revise that well. Combination of cells, right? You identified the question already because we revised this question. I think this kind of similar questions we did before also. A 10 volt a cell of negligible internal resistance is connected in parallel across a battery of EMF 200 volt and internal resistance 38 ohm as shown in the figure. Yes, see here this is end-to-end combination. It is a series combination. See, one end of this is connected to the other end of the cell. We know that is how series combination can be connected, right? End-to-end connection. So the only thing you have to remember, when cells are connected in series, E equivalent is equal to E1 plus E2. That is series combination equivalent EMF. Look at the question. You are asked to find the value of current in the circuit. Current in the circuit is going to be, yes, so current in the circuit always is going to be total EMF divided by total resistance. Yes. That is a current in the circuit, right? Fine. So only thing you have to calculate here is E equivalent. R equivalent we don't have to calculate much because only one resistor is given. That is your R equivalent. Good. And one more point you have to be careful. Anybody identified what will be E1 plus E2 in this question? Anything wrong with the connection? I'm giving you a clue, a hint. Yes, see 200 volt. Yes, Karthik. Exactly, you found out. 200 volt and 10 volt cells are connected in such a way that positive of the first cell is connected to negative of the second in the actual connection. But in this diagram you can see positive of the first cell is connected to the positive of the other cell only. So that is called a reversed cell, right? So when you go for reversed cells, you know, equivalent EMF is not E1 plus E2. At that time it is E1 minus E2. Yes, so this is a reversed cell. Be careful when we get cells combined. It's a series combination we identified, but it is a reversed cell, so E1 minus E2. So what is E equivalent in this case? It is not E1 plus E2, it is E1 minus E2. So 200 minus 10, which is going to be 190 volt. So now calculation of current is not difficult. I is equal to 190 by 38 because that is the only resistance connected in the circuit. So this will be 5 ampere. That's the answer. See, two things you know, like series combination, what is equivalent, and most important, it is not a like normal series connection, it is reversed cell connection, so E1 minus E2. Okay, so then we will move on to the next one. Two cells of EMF 1.5 volt and 2 volt having internal resistances 0.2 ohm and 0.3 ohm respectively are connected in parallel combination of cells. Let me tell you in between. Parallel combination of cell, that equivalent EMF derivation is one of the most important derivation from this chapter. Revise that, okay? Learn well. Then they are connected in parallel. Calculate EMF and internal resistance of the equivalent cell. See, if you know the equation, this question is not at all difficult. We know when we connect two cells in parallel, equivalent EMF is going to be, this is E1, this is E2 EMF, resistances R1 and R2. E equivalent of this combination will be E1 R2, correct? E1 R2 plus E2 R1 divided by R1 plus R2. Yes. And one more thing. See, unlike in series combination, when we come to parallel combination, positive terminals are connected together to one single point. negative terminals are connected together to the other point, right? Yes. So, but in series combination, plus connected to minus. That's the actual connection, right? But here it is the other way around. Okay, hope you note those differences. Direct substitution only. We are given all the values. See, what is E equivalent? Let us just simply substitute and simplify. 1.5 is the first EMF, and what is the next? 1.5 into 0.3, right? 1.5 into 0.3, E1 into R2, not R1. Yes, plus E2, 2 into 0.2, right? The whole divided by 0.3 plus 0.2. Yes, that's it. So we will get, this is 0.45, correct? Plus this is 0.4, the whole divided by 0.5. We get 0.45 plus 0.4 is going to be 0.85 divided by 0.5, which will be double of 0.85, which is going to be like 1.7, right? Volt. That is equivalent EMF, right? So equivalent EMF is easy. We just substitute and simplify. Okay, cross check the calculation to make it correct. And how will you calculate EMF? Equivalent internal resistance, that also to be calculated. Correct? Equivalent EMF. Resistance. It is 1 by R equivalent is equal to 1 by R1 plus 1 by R2. We know it is R equivalent is equal to, what is that? R1, R2 divided by R1 plus R2. Parallel combination of resistances, substitute 0.2 and 0.3 there, that's it. Okay, nothing much to do. So I am leaving that to you. Since R1 is going to be 0.2 into 0.3 divided by 0.5. So 0.06 divided by 0.5. So we get 0.12 is the resultant internal resistance. Okay, fine. So that is direct substitution, so we don't have to waste time on that question. Yes, here comes the Superman. Kirchhoff laws, right? Using Kirchhoff rules, calculate current through 40 ohm and 20 ohm resistors in the following circuit. You are given a beautiful circuit here. You are asked to find what are the current through 40 ohm and 20 ohm resistances. Identify those resistances first. See, 20 ohm resistance is here, so a current is flowing through that, that is to be calculated. Second one, 40 ohm resistor, that is the RBC, right? Sorry, DC. That current is to be calculated, easy. Right? It's a direct application of Kirchhoff law and simplifying it. I'll just start with the marking of current. We have given two cells here, right? So I will take a current from the positive terminal. One thing I just want to remind you once again, these network, like in the paper, question paper, the network will be given. To solve it, we have to mark the current. So usually we draw that diagram in the paper. Answer sheet, I mean. Yes, when you draw that diagram in the answer sheet, cross-check again and again whether you marked the terminals of the cell properly as given in the question. Okay, because if the slip that cell is flipped, done. Whatever value you substitute properly, whatever sign convention you apply properly, your final answer is wrong. So be careful, cross-check the circuit once and twice, then make sure you are doing it properly. Then let me mark one current flow starting from the positive terminal of this cell. I will take it as I1. Okay, see, or always we say like we have a greater voltage cell, 80 volt cell is given here. From the positive terminal of 80 volt cell, let me take my current, I1. When I mark a current in a branch, one single branch, one single current, yes, I1 is flowing throughout in this branch up to the point C. So I1 is the current in that branch. One branch, one current, right? Good. From the positive terminal of this cell, let me mark another current, I2. Okay, I2. That I2 flows through this branch, one current, this will be I2. Yes, I2. We have one more branch remaining. What happened to the current at this point? See, I1 is coming to the junction rule, right? Current is entering to this junction C. Venkata, can you please check your answer? Somewhere you got a mistake, so please cross check it. See, this current enters the junction here C at C, and that current, from that current I2 is gone, right? I2 is gone. So what is the remaining current? This current is going to be from I1 I2 is gone. Remaining current is I1 minus I2. That current will be flowing through this branch. So look at that. Now the continuity of current starting from here, this current flows through this, that is completed. Yes. And this current, I1 minus I2 comes here. It splits into, I1 comes here and it splits into I1 minus I2 and I2. And this is the way how it is flowing, right? The total flow of current. The continuity is maintained and cross-check the branches. We don't have any opposite currents in one branch, one current only. Yes, done. And we neatly marked the current in the circuit. That's the first step if current is not marked. We have done that. Okay. Now as per the question, we have to find out the values of I1 because I1 is the current flowing through 20 ohm and I1 minus I2 flowing through 40 ohm. So basically we have to find both the current I1 and I2. Okay. Let us quickly apply. See, I am following some loops. If you follow the same, you can cross check later and follow your sign convention convenient for you. Okay. Yes. Who is that? Yes, Anj. That is correct. And tell me the other current also. Okay. Just proceed. Let me go for the first loop A, B, C, D, A. Okay, so I'm going for loop A, B, C, D, A. We'll do this question in detail. That's it. So from A to B, let me apply my sign convention. I'm going for minus 80 plus 20 I1. Right, so I reached the point B. From B to C, nothing. And from C to D, we have plus 40 I1 minus I2. That's it. That is equal to 0. Correct? Yes. So we can say 20 I1, 40 I1 is going to be 60 I1, right? And see 40 I2 minus 40 I2 is equal to 80. I'm taking 80 to the other side. Yes. And we can divide this by 20. So we will make that equation smaller. 3 I1 minus 2 I2 is equal to 4. Equation number 1. We need one more equation because to solve two variables, we need two equations, right? Okay. So find out 3I1 minus 2I2 is equal to 4. That is first equation we got. Let me go for the outer loop now. A, B, C, F, E, D, A. You can take any loop. Let me just go for loop A, B, C, F, E, D, A. Yes, I'm skipping that mid part, like that branch I'm skipping. So starting from here, once again, I get minus 80, like plus 20 I1. And we reached B, between B and C nothing, and we reached F, nothing to be done there, and from F to E when we come we get plus 10 I2 minus 40 equals to 0. Correct? Yes. See, look at this, we have 20 I1 and yeah, so that's only 20 I1 plus 10 I2 is minus 120 equal to 0, or I can say 20 I1 plus 10 I2 is equal to 120. You can simplify that further, right? So I will write dividing throughout by 10. Yes, so we get what? I1, say 2 I1 plus I2 equals to what? Yes, Smriti. Fine. So you just proceed, and this is going to be 12, right? This is equation number 2. Yes, done. So we have 3 I1 plus 2 I2 plus 4 equals to, equal to 4 is equation number 1. This is equation number 2. Sorry, equation number 2. Yes. Now find a way to simplify them. So we have 2 I2 here, minus 2 I2. If we just multiply this one, with 2, we can easily solve it. I'm just going to multiply equation number 2 with 2. What will I get? 4 I1 plus 2 I2 plus 2 I2 equals to 24. This is my equation number 3. Now just add equation 3 and 1. You will get one of the currents. Easy. See, what is your equation number 1? 3 I1 minus 2 I2. Here we have a plus 2 I2, correct? Yes. When you add them up, what about the I1 part? 4 I1 plus 3 I1, we get 7 I1. Good. 7 I1. But what about 2 I2 part gets cancelled? One is plus 2 I2, the other one is minus 2 I2. That is gone, and 24 plus 4 we get 28. See, I1 is obtained. What is your I1? I1 is going to be 28 by 7, which is 4 ampere. Good. Yes, some of you solved already. Yeah. 0 ampere, and yes, I2 is not 0. The other current, cross check that calculation. I1 is going to be 4 ampere, right? Now substitute that I1 in any one of those equations, you will get I2. And we need only the values of I1 and I1 minus I2, okay? These are the values we have to specify, because we have to find out what is the resistance, what is the current across 20 ohm resistance, which is I1. This is across 40 ohm resistance, which is I1 minus I2. So for that, we have to find out I2 also. Can I do here? If you substitute I1 in equation number 1, so 3 into 4, right? I1 is 4 ampere minus 2I2 equals to 4. So we get 12 minus 2I2 equals to 4. So 2I2 is going to be 8. I2 also found to be 8 by 4, which is 4 ampere. Yes, surprisingly I1 and I2 are equal. So we got I1 is equal to 4 ampere. Yes. No. Many of you have some problem with the calculations. Be careful, okay? Apply sign convention properly. 1 ampere and 5 ampere. No. Look at that. I1 and I2, both of them are 4 ampere each, okay? Yes, that should be the answers. I1 is equal to 4 ampere, I2 is equal to 4 ampere. Exactly, yes, Venkata. Fine. And yes, Mohammed Hisham. Definitely I1 minus I2 will be 0 because both of them are equal. So we got I1 as 4 ampere. I2 also has 4 ampere. So your final answer, be careful when you answer this question, we need only I1 and I1 minus I2. I1 is 4 ampere. So when you write the answer, current flowing through, yes, you just write it here, current flowing through 20 ohm resistance. From the figure it is I1. I1 is 4 ampere. First one you answered. Second one, current flowing through 40 ohm. That is going to be I1 minus I2, which is I1 minus I2 is 4 minus 4. Finally, we got 0 ampere, which means there is no current flowing through the branch DC in the network, okay? So be careful, apply sign conventions properly. Don't be in a hurry, okay? Just take your time to solve this. And easily, like, when you are in a hurry with the sign convention, like especially, plus and minus, if it is reversed, done. You will not end up with the correct answer, so be careful. Yes, okay, fine. Moving on to the next. So that was a detailed discussion of that network, because in the next one, it is an easy one, so we don't have to explain this much. That's why I did this part detailed, okay? Again, it's a Kirchhoff law question, but it's a different way. Use Kirchhoff rule to determine the potential difference between the points A and D. See, A and D, where no current flows in the branch BE, in the BE of the electrical network shown in the figure. So you are asked to find VD minus VA, correct? VD minus VA. Potential difference between A and D. Yes. See, when you go through this network, you can find it out in different way. See, usually whenever you are asked to find out potential difference between 2 points in a network, we will take one branch and we consider that as a closed loop. Yes, so you can reach the point D from A in 3 different paths. See, this is one path, like A, F, E, D. You can reach D there. Similarly, you can go from A, B, C and reaching D. Or A, B, E and D. And I prefer the third one. You know why? Because the question says there is no current flowing through the branch BE. See, R1 is unknown, R is unknown. We don't know both the values, and also current in the circuit is unknown. You can calculate current in the circuit, you can calculate R using Kirchhoff laws, but you can solve this question in an easy way without finding that current. Like you can go or resistance, unknown resistance. You can solve this starting from A if you follow this path. Look at this. We have a resistor R1 here. We don't want that resistance R1's value because current flowing through this branch is 0. So that resistance is dead. It doesn't have any potential drop across it, right? Yes. But we get 2 cells and we have to find out the resultant of that. That's it. Okay. So if I redraw this network starting from A, right? This is the point A and we have a 6 volt cell. This is the point B and we have a 3 volt cell there. And R1 is neglected because there is no current acting on it. This is the point E and we reach the point D here. See, this is the point D, A. And potentials of these cells given like this is 6 volt and this is 3 volt, correct? Yes. See, now imagine this as a closed loop so that potential at the point A is VA, potential at the point D is VD. If you take VA as plus, take VD as minus, or take VD as plus, VA as minus. So both are fine. Imagining they have a potential difference, and that potential difference we have to calculate. Okay, yes. So I prefer this path A, B, E, D. See, look at this A, B, E, D. Now if I start from A, see this point has a potential difference VA in 2 steps. Now we will get the answer. See, I will go for that. VA, I have taken VA as positive. Okay, then I am getting a 6 volt cell in my path. So I have plus 6. Then when I reach it B, going up again, one more cell plus 3V, 3 volt, and I reach it E. See, I neglected the resistance because there is no current. It has no effect. It has no influence in that circuit. So it reaches E. Now minus VD is equated to 0. Correct? Yes. So what is this? VA minus VD plus 9 equal to 0, or VD minus VA equals to 9 volt. See, in 3 steps we get the answer without finding current or unknown resistances. Got it? Yes. So only because we have given an information BE is free from current. That's it. Right? And I can show you one more thing here. We have, this is a combination of cells only, series combination of cells. When you just stretch this branch, you know, A and B, these are the 2 points, A and D. I am stretching that branch, you know, starting from here, we have one cell, 6 volt, one more cell, 3 volt, nothing more in between. So 6 volt, 3 volt connected in series, end to end, proper connection. 6 plus 3 will be 9. That is the equivalent EMF, equivalent potential difference we have, right? Yes. Okay. So since it is given to solve as using Kirchhoff laws, we use this loop rule here. Fine. Okay, so that is the end of those questions. Now, the long answer question also mentioned here, just like in the previous chapters. Let us just quickly run through it. Find relation between drift to velocity and relaxation time. Okay, see, in understanding relation or like influence of temperature on resistance and resistivity, see that part, this relation is about drift to velocity was the key concept there to understand that. And we had a relaxation time tau, which is the average time between 2 successive collisions, we know. So that relation, drift to velocity equation they are talking about, yes. Fine, then a small new question, a conceptual question related to that is also given. So that derivation of drift to velocity equation you just revise. Then drift to velocity of electrons you have to define, and then obtain relationship between current density and drift to velocity of electrons. Current density, we know the term I by A, and drift to velocity. Basically, we have to derive that equation I is equal to NAV drift to velocity. If you take this A to the LHS, that is current density, okay? So this equation derivation is very, very important. Just revise that. See, the next question is directly that equation only, the or question given. I is equal to NAEVD relation to obtain. Okay. Then, yeah, I told you before when we came to a question like this, parallel combination of cells, right? Yes, that parallel combination, equivalent EMF and internal resistance question that you revise, you must have learned that particular part. Okay, that was end of current electricity part. Okay, we have to move to magnetism, sir.
Yeah, ready.
Let's proceed.
Thank you.
Yes, okay.
Yes, good evening once again. Now we are 26 questions is already completed.
Yes.
24 more questions are there. Already we have completed 2 hours 15 minutes. Thank you for your patience. First of all,
Thank you for being with us.
Yeah.
Yeah, and we
so we try to finish it quickly. Current electricity and electrostatics, you know, there are questions. It will take a lot of time.
Exactly.
Time-consuming questions. We'll try to wind it up quickly. Okay, so
go on, sir.
moving charges and magnetism. So look at the topics. First, magnetic force is there. Motion in a magnetic field, combined electric and magnetic fields. So Biot-Savart's law, circular current loop. So check the 10-year paper analysis. Look at this one, the second one. What is the second one? Motion in a magnetic field. Motion in a magnetic field, you can see that force experienced by a charged particle moving in a magnetic field. That is Lorentz force. Lorentz force questions is very important. Lot of questions been asked. Then fifth one, what is the fifth one? Circular current loop. Magnetic field to a circular coil. The derivation for 5 mark they can ask. Then numerical based on that, we will discuss that. Then eighth one, force between 2 parallel current carrying conductors. Derivation is there. Numericals are there. And ninth one is torque. Then galvanometer based question. That means conversion of galvanometer to a meter, like current sensitivity of galvanometer, many things. Okay, so we are going to start our questions from moving charges and magnetism. Check one by one. Now, as per our order, it is question number 27. A straight wire of mass 200 gram and length 1.5 meter carries a current of 2 ampere. It is suspended in mid-air by a uniform magnetic field B. What is the magnitude of the magnetic field? See, a straight wire of mass 200 gram. So you can take a straight wire. This is a straight wire. Its mass is given as 200 gram. 200 gram wire. Length is 1.5 meter. Carries a current of 2 ampere. So I is equal to 2 ampere. I is equal to 2 ampere. It is suspended in mid-air by a uniform magnetic. So what is the logic of this question? Suspended in mid-air. A body is suspended in mid-air means you know that if you are keeping a body like this, the weight will be acting down always. So suspended in mid-air means that weight should be balanced by some force. Then only you can suspend a body. So here which force can balance this? Magnetic field. You know that when a current carrying conductor is kept in a magnetic field, that conductor will be experiencing a force. If that force is equal and opposite to the weight of the body, weight is acting down, that weight is balanced by what? Magnetic force. So suspended means it has to be equal. That means the weight of the body should be equal and opposite to the magnetic force. So you know the expression for force on a current carrying conductor when kept in a magnetic field. So just equate. So weight means if m is the mass, what is weight? mg. What is the expression for force experienced by a current carrying conductor? Do you remember? F is equal to I into L cross B. This is the formula, isn't it? I into L cross B, or it is equal to ILB sine theta. This is the expression for the force experienced by a current carrying conductor. Yes or no? So we can just equate weight of the wire mg is equal to ILB. Okay, so here it is given uniform magnetic field. So theta value is not mentioned. So we can just assume that we are applying magnetic field in such a way that maximum force is obtained. So that sine theta value has to be taken as 1. So we get mg is equal to ILB. What they are asking, B value. So you can easily calculate it now. It will be mg by IL. Substitute what is mass? 200 grams. So it is 200 into 10 to the power minus 3 gram into kilogram. G I am taking 10 by current is 2 ampere. 2 ampere into length. What is the length? 1.5. Okay, 1.5. Now we can easily solve this. 2 got cancelled. 10 raised to minus 3 and 10 into 100 will become. So it will become 1 by 1.5. 1 by 1.5 means 3 by 2. 2 by 3, isn't it? 2 by 3 Tesla is the answer. How many of you got this? Yeah, 0.66. Very good. Smriti, Saj, Adamson. All right. Yes, Ashmita, correct answer. Can I go to the next? So please note this. F is equal to ILB. Sine theta is the formula. And one more thing. How can you find the direction of this force experienced by a current carrying conductor? You know we have to use Fleming's left hand rule. Important, Fleming's left hand rule to find the direction of force experienced by a conductor or a moving charge particle. What is left hand rule? In forefinger indicates magnetic field, middle finger indicate current, then the thumb will give you the force. Okay, so very, very important topic, force experienced by a current carrying conductor. Let me go to the next question, question number 28. Question number 28, look at that. Write an expression for the magnetic force acting on a charged particle moving with velocity v in the presence of a magnetic field. So that is a direct question, Lorentz force experienced by a charged particle. F is equal to QVB sine theta, Q into V cross B. This expression, that is the first question. This is a 3-mark question. First time it is asked in 2016 board exam. Write the expression for the magnetic force acting on a charged particle moving with a velocity V in the presence of a magnetic field. So that is an easy question, Q into V cross B. What is the second question? Look at this. A neutron, an electron and an alpha particle moving with equal velocities enter a uniform magnetic field going into the plane of the paper as shown. Trace their paths in the field and justify your answer. Justify your answer. My dear students, in Lorentz force, we have different possibilities. In this equation, theta is the angle between V and B. You know that if a charged particle is going parallel to the magnetic field, theta value is 0. Anti-parallel to the magnetic field, theta is 180. In both the case, we get force as 0. That means the charge will move without any deviation. And what is the other possibility? If theta is equal to 90 degree, it follows a circular path. Remember or not? Very, very important idea. If theta is equal to 90, force will be maximum and charge follows a circular path. And in such circular path, we have an equation for radius. Hope you remember the formula. The radius is mv by qb. How did you get that formula? Do you remember? See, if it is moving in a circular path, surely it will have centripetal force. You know the formula for centripetal force, it is mv square by r. That centripetal force formula you can equate with the Lorentz force formula. Mv square by r is equal to qvb, and simplifying it you get r is equal to mv by qb, important equation for the radius of the circular path. And at the same time, one more case was also there, like if theta is in between 0 and 90, what was the shape of the path followed? It's a probable multiple choice question. If theta is 90, circular. If theta 0, straight without any deviation. Theta 180 is also straight. What about if theta between 0 and 90? It follows a helical path. Hope you remember all of this. Like now, mv by qb. So it follows so here you can check what is the direction of magnetic field. It is into the plane of the paper. It is directed inward. Yes, directed inward. And all alpha particle, neutron and electron all are entering, moving towards right. So what is the value of theta? Without any doubt, we can say that theta is equal to 90. Theta is equal to 90. So these particles are expected to go in a circular track. But there is neutron. Neutron. Can you tell me what will happen to neutron? What will happen to neutron? Will there be any change in its path? Any change in its speed? For neutron? No, right? Because neutron does not carry any charge. This force formula is applicable only for charged particle. That means neutron will go straight without any deviation. Neutron will go straight. Now, alpha particle and electron, here they are not asking us to calculate what is the radius, only to trace the path. So that's enough. You know that it will be in a curved path, it follows a circular path. The only question here is, in which direction? So for that we can simply use left-hand rule. Left-hand rule, you know that if positive charge is moving, that is the direction of current. That means if positive charge is moving towards right, direction of current is towards right. If negative charge is moving towards right, then the direction of current is towards left. So let's take alpha particle. What is the charge of alpha particle? Charge of alpha particle is, alpha particles are positively charged particle, you know that, isn't it? So what we get, see, these alpha particles are going towards right. So what will be the direction of current? Current will also be towards right. And direction of magnetic field is inward. So look, I am going to apply left-hand rule. In exam hall, you have to do like this. You have to apply left-hand rule. So no need to worry. Anybody sitting on your left side or right side, you can freely use your hand rules because there are many hand rules, you know that. So check, what is the direction of magnetic field? Is into the plane. Into the plane, and current is towards right. So look at my thumb. What's the direction? It's upward. So what will happen to alpha particle? Alpha particle will go up. That means the path here only, magnetic field is till that point only. So no need to show the entire curved path. You can just show the alpha particle will be going like this. That's enough. Okay. Alpha particle will be going like that. As I can see the comments, Saad, see, don't feel bad like I'm not getting enough time to go through all the comments. Anyway, you keep on commenting because that's our energy, because we started, you know that at 5 o'clock. Tomorrow also we'll be having sessions. So keep on commenting. I'll try to give response to all the comments. Yes. And now what about electron? Electron is moving towards right. So electrons are moving towards right means the current will be towards left. So you can see that if positive charge is going up, surely the negative charge will be going down. So I hope this is clear. Yes or no? Lorentz force, my dear students, question will come from this topic. Okay. Yes. I am going to the next. Okay. So justification also they are asking that you can easily write neutron. Why neutron moving straight means no charge, so the force will be 0. Okay, right. Now question number 29. Question number 29. Two long straight parallel wires. It's an important question. Important question, repeating one. Two long straight parallel wires A and B separated by a distance D carry equal current I flowing in same direction as shown in figure. Find the magnetic field at point P situated between them at a distance x from the wire. So here the diagram is a bit confusing. Actually, what does this point indicate? This is a cross-sectional view of the conductor. It's like two conductors only. So instead of drawing like this, we can draw a clear view of this. What is the meaning of that diagram means? There are two conductors. Look, this is the first one. And there is one more conductor like this. So this same thing only, it is shown in a different way, like in a top view of the conductor is shown. That's why it looked like 2 points. The cross-sectional part is shown. Okay. Now these two conductors are carrying currents in what? The same direction. So this one is carrying a current. This is also what? Carrying current. Same current is given, I. Okay. Right. Now what they are asking, find the magnetic field at a point P. P is here in your diagram, and you can see it is at a distance of x. What is the total distance between these two? It is given as what? D. P is at a distance. P is at a distance x from first conductor. So x. So surely what will be this distance? It will be d minus x. D minus x. What they are asking is finding the magnetic field at that point. Magnetic field at that point. First question is, how many fields will be there? There are two conducting wires. Around every current carrying wire there are magnetic fields. So here two wires are there, means surely there will be two magnetic fields. Recall the formula. Recall the formula. What is the expression for the magnetic field due to a straight conductor? Tell me. Magnetic field due to an infinitely long straight conductor formula is mu naught I by 2 pi r. Isn't it? B is equal to mu naught I by 2 pi r. You know, this is the formula for the magnetic field due to a straight wire. So here, since there are two wires, there will be two magnetic fields. So I am just naming this as a first conductor and this as a second conductor. So we will be having two magnetic fields, one due to the first one and other due to the second. So let me write B1, magnetic field due to the first one. How can you write the formula? It is mu naught. What is the current? Current is I by 2 pi. What is the distance? From the first conductor, the distance is x. So look at that. B1 is equal to mu naught I by 2 pi x. Yes or no? Yeah. And what will be B2? Magnetic field due to the second conductor. Same current, mu naught I by 2 pi into, what is distance? D minus x. Right. D minus x. So we got both the magnetic fields. Now check. Field is a vector quantity. So whenever you are calculating the resultant field, you need to check the direction. Tell me, which rule? Which rule? Right hand thumb rule. So can you answer my question? What will be the direction of magnetic field at P due to the first conductor? Due to the first conductor, whether the field will be inward or outward. First conductor is carrying current in upward direction. So what is the direction of magnetic field at P? Yes, Ashmita, right answer. So it will be inward. Magnetic field due to the first conductor will be inward. And what about the second one? Second one is, it's also carrying current in upward direction, but the point is on the left side of it. So if you are keeping our thumb rule, like you can see the field is out. So one thing is sure, both the fields are oppositely directed. One is inward and other is outward. So how can you find the resultant? It is vector sum, bigger one minus smaller one. So I am going to subtract. So the resultant magnetic field B is equal to, we can write it as B1 minus B2. B1 minus B2. Got it? Yes. So B1 minus B2 means you can see mu naught I by 2 pi is common in both. So we can write 1 by x minus what? 1 by d minus x. So this is equal to mu naught I by 2 pi into, I can take x into d minus x as LCM. So we get d minus x here minus what? X. So it is B is equal to mu naught I by 2 pi into d minus 2x divided by x into d minus x. D minus x. Alright. So this is the formula. This is the magnetic field. This is the magnetic field. Okay. Yes. Clear or not? This is the magnetic field at the center. I mean, not at the center, at a point, point P at a distance x from the first conductor. Is it okay or not? Right. So that is the answer for the first one. Now there is a second question. Look at that. Show graphically the variation of the magnetic field with distance for x. X's lying between x's, you can see 0 less than x less than d. So 0 less than x less than d means we need to start from here. So x is the distance from here. So this is at this point, what is x? 0. So here x is equal to d. So how that magnetic field is varying? So you just think at the midpoint, what will be the magnetic field, my dear students? At the midpoint, can you tell me? At the midpoint, the magnetic fields will be equal and opposite. So what will be the magnetic field at the midpoint? It will be 0. 0. Okay. So I am just marking the mid region here. So surely at the midpoint, the magnetic field will be 0. 0. Now you have to answer my question carefully. If the point P is left of the midpoint, which magnetic field dominates, B1 or B2? If the point is on the left side of the midpoint, B1 or B2, then we can easily find the answer for the second one. We can easily draw the graph. If the point is on the left side, which field dominates? B1 will dominate, no? B1 will dominate because the distance is small. Yes, B1 dominates. And remember, we already found the direction of magnetic field. It was inward. Due to first conductivity is inward. So inward field dominates. Yes or no? Right. Now if the point is to the right of the midpoint, which field dominates? B2 will dominate. Yes or no? That means the direction of resultant field is outward. That means to the left of the midpoint, the field will be in, and after that it's out. That means here x is gradually increasing. When x reaches d by 2, the field will be 0 at the midpoint. So I am going to draw the graph. Okay. See here, I am going to take x. When x becomes d by 2, you know the field is 0. When x is equal to 0, what is the field? You can check. If you are substituting x is equal to 0, we get how much? If x is 0 means denominator will become 0. So the magnetic field will be infinity. So close to that point, that means x is equal to 0 means the field will start from infinity. And if x is equal to d also, we get d minus d, that will also be 0. So when x is equal to 0, the field is infinity. When x is equal to d also, what? The field is infinity. And you know that after the midpoint, the direction is getting reversed. So the graph will be like this, dear students. Here it is infinity going like this, and from that point it has to change its reverse direction and it will be going like this. This will be the shape of the graph. Understood or not? So here you can see at here x is equal to 0, infinity. X is equal to d by 2, it's 0. So left side, right side, the direction is changing, and here it's again infinity. Yeah, kind of like a parabola. Not perfect. Yes, shiny, like, yeah. Is it clear or not? Can I go to the next question? Can I go to the next question? Please comment. Please comment. Is it okay? I hope it's clear for you. Yes. So we are going to question number 30 now. Question number 30. Two identical. It's a repeating question. You can see that. There may be changes in the value of current and the radius and all, but it's a repeating type question. Look at this. Two identical coil P and Q, each of radius R, are lying in perpendicular planes such that they have a common center. Find the magnitude and direction of magnetic field at the common center of the two coils if they carry currents equal to I and √3I respectively. Tell me, students, magnetic field due to a circular coil, what is the formula? Magnetic field due to a circular coil, we have an equation like if this is a circular coil at a distance x and this radius is a, so we have a formula B is equal to mu naught I a square by 2 into a square plus x square whole raised to 3 by 2. This is the expression for the magnetic field due to a circular coil. And at the center of the coil, what is the formula? At the center we have B equal to what? Mu naught I by 2r, where r is the radius. Mu naught I by 2r. Okay. Yes, Imran is asking how many chapters we are going to. Imran already told you, like at the beginning, we are going to cover till alternating current in this session. Okay, alternating current. So we have like 20 more questions. Okay, it won't take this much time because as I told you, the previous chapters, current electricity and electrostatics, took a lot of time. So I'll try to finish it up quickly. So mu naught I by 2r. Okay, so if you are listening these questions carefully and doing it and trying to understand this, the board exam will be very easy. Because we have included all probable questions. We analyze the last 10-15 years papers, and from that only the selected questions and related concepts we are explaining. So don't think that it will be a wastage of time for you. Okay, so be focused. Come back. So there are two coils and they are mutually perpendicular. If coils are mutually perpendicular, what do you think about the magnetic field? They will also be mutually perpendicular, right? So we have to find the field separately. So first I am taking B1. B1 mu naught I by, what is the current? First current is I, second current is √3I. Radius is R. So I can write B1 is equal to mu naught I by 2R. This is B1. Okay, yes. And what about B2? B2 will be mu naught. it is root 3I. So instead of I can write root 3I by what? 2R. We got both the magnetic fields. Now if you are comparing these two, you can see that B2 is equal to root 3 times what? B1. Because B1 is mu naught I by 2R. This is root 3 into mu naught I by 2R. So B2 is root 3 times B1. Now we have to find the magnetic field at the center. So since the coils are arranged like this, mutually perpendicular, the field will also be perpendicular. You know that you can apply right hand palm rule. If the coil is carrying current like this clockwise, the field will be inward. So same logic if you are applying, you can mark. The P is like this, P is carrying current like this, so field due to P will be in upward direction. Okay, P is the first one, it is carrying I, so B1 is upward direction. This is field due to P, and B2 will be, B2 is carrying current like this, yeah. This is the direction of B2, they will be mutually perpendicular, so like this. Okay, so you know that if two fields are there, we need to find the vector sum of these two fields. But here, they are not in the same direction, they are not in opposite direction, so how can you find? Vector sum formula, root of a square plus b square plus 2ab cos theta. But what is theta value in this case? What is the angle between b1 and b2? 90. So we get root of b1 square plus b2 square. So resultant field B is equal to square root of b1 square plus b2 square. Yes or no? So it is equal to square root of b1 square plus b2 already we found root 3 b1. Squaring we get what? 3 b1 square. So we get it as 4 root of, it is equal to square root of 4b1 square, that is equal to 2b1. 2b1, you can substitute 2 into, what is b1 value? Mu naught I by 2r, 2 got cancelled, so finally we got the expression B is equal to mu naught I by r. This is the magnitude of the magnetic field. Yes, magnitude of magnetic field, mu naught I by r. Okay. We can't expect the same question. In questions they may give different radius, different current, so like that many possibilities are there, but you have to understand the concept. What we are doing, we are finding field due to both the coils, checking their directions, finding the vector sum. So here they are asking magnitude. Okay, we got the magnitude, mu naught I by r. And what about direction? Direction, how can you mark? Direction, instead of writing in words, you just draw this diagram in your answer paper. And two vectors are acting like this. How can you find the direction? Vector sum. So just complete the parallelogram, you know parallelogram law, and draw the diagonal. Like this is what? The resultant direction, you know that. So this is B. And we need to find that direction. How? Direction, you know that in vector addition, we have to find direction in terms of an angle. So you can just mark this angle as phi or theta or anything. Then how can we find phi? For that you can take tan phi. So I am answering the direction part. So from that diagram you can write tan phi is equal to, tan is opposite side by adjacent side. So what is opposite side? It's this side, that is B1 by B2. So tan phi is equal to B1 by B2. So which is equal to B1 by B2, we got it already. What is B2? Root 3 B1. Root 3 B1. So B1 got cancelled, we get 1 by root 3, 1 by root 3. This is tan phi, tan phi. So if tan phi is 1 by root 3, what is phi? Phi will be equal to tan inverse 1 by root 3, 30 degrees. So 30 degree is the direction of magnetic field. So as a final conclusion, you have to write the resultant magnetic field will be making an angle 30 degree with B2. 30 degree with B2. Is it clear or not? Yes. Clear, right? Yeah, Ashmita, right, pi by 6, or you can write 30. I hope this is also very clear. I'm going to the next question, question number 31. 31, again an important question. Important question, look at this. A square loop of side 20 centimeter carrying a current of 1 ampere is kept near an infinite long straight wire carrying a current of 2 ampere in the same plane as shown in figure. Calculate the magnitude and direction of the net force exerted on the loop due to the current carrying conductor. I think by seeing the question itself, you got an idea based on which topic. Force between two parallel current carrying conductors. So here, like, again the diagram is given horizontally. We can make it vertical. Then only we'll feel that the question is very simple. So let me show that straight conductor like this. Okay. And there is square loop. That square loop I'm going to keep here. This one is carrying a current of what? 2 ampere. 2 ampere, and this loop is carrying 1 ampere current. This side is 20 centimeter, yes, 20 centimeter, and this distance is given as 10 centimeter. They are asking the net force acting on that loop. So you know the logic, like what is the formula for force between two parallel current carrying conductors? If first conductor is carrying current I1 and second one is I2, you know the force formula is F is equal to mu naught I1 I2 by 2 pi r into L, length of that conductor. Force experienced by the conductor of length L is this one. So here what you have to note is, you can see that this conductor and this conductor are parallel conductors. Both of them are carrying currents in upward directions. So there will be, please note, very important, if currents are in the same direction, the force will be attractive. If currents are in opposite direction, the force will be repulsive. So since these two are carrying current in same direction, these two wires will attract. This wire and this wire are carrying current in opposite direction, they will repel. Okay, so we have to find these two forces separately and take the vector sum. That's what we need to do here. This is a simple question but repeating. So first of all, I'm going to find the force between this wire and this one. That force I'm marking as F1. So F1 is equal to mu naught I'm writing it. What is I1? 2 ampere. Mu naught I1 is 2. What is I2? 1 ampere by 2 pi into r. R is the distance. Distance is 10 into L. What is L? L is length of this wire. Length of this wire. It's a square loop, so that will be 20. You may think that why I didn't convert that centimeter into meter. Here you can see that this 20 is in centimeter, this 10 is also in centimeter. So if you are converting in meter also, anyway it will be cancelled out. So calculation will be simple even if you are not converting. So I am just cancelling it out. So what I can see is this 2 and this 2 will be cancelled. Mu naught value, you know that it is 4 pi into 10 to the power minus 7. Now is remaining there like a 2 and pi. So we get 8 into 10 power minus 7. This is F1. F1 is 8 into 10 power minus 7. Now what you need to note is what is the direction of this F1. These two conductors are carrying current in the same direction, so surely they will attract. So this wire will be attracted. So F1 direction is towards left. Towards left. Now you can think about this one and this one. That force we can take it as F2. So let's calculate F2. F2 is equal to again mu naught, that is 4 pi into 10 power minus 7. Minus 7. I1 there is no change. I1 is 2 ampere. I2 there is no change. I2 is 1 ampere. Length there is no change. It is 20. Distance there is change. Distance between this wire and this wire is 10 plus 20, 30 centimeters. So denominator will become what? 30. Okay, now we can solve it. 2 pi r is there, so 2 pi into 30. This got cancelled, 2 and 2 got cancelled, this cancelled. So what are the remaining terms here? 2 into 4, 8 by 3 into 10 to the power minus 7. 10 to the power minus 7. So that is the force on the second wire. Okay, we got F2. Now what is the direction of F2? Currents are in opposite direction. See, this is upward, this is downward, this is carrying current up, this is down. So what will be the nature of the force? It will be repulsive. That means F2 will be acting in this way. F2 will be acting in this way. So we got an idea, total force, one is towards left, other is towards right. Now the question is, which one will be bigger? Comment please. F1 or F2? Which is big here? F1 is towards left, F2 is towards right. And that's a simple logic, isn't it? Distance is small for F1, so F1 is greater than F2. So the resultant force will be what? F1 minus F2. F is equal to F1 minus F2. So what is F1 value? 8 into 10 power minus 7. Minus 7. Minus 8 by 3 into 10 power minus 7. So 8 into 10 power minus 7 will come out. We get 1 minus 1 by 3. So 3 minus 1, 2 by 3. So 8 into 2, 16 by 3 into 10 to the power minus 7 Newton. This is the answer. Yes or no? Yeah. Please comment, is it clear or not? Yes, I can see like Kavi, Venkata, Ashmita, Salman, Asim, Nashiappan, Bhaskar. Yes. Thank you very much. Yes. Yeah, Ashmita 5.3 something you'll get, right? Yeah, Tanvi. All right. Yes. So I'm going to the next question number 32. 32. Look, a square-shaped plane coil of area 100 centimeter square of 200 turns carries a steady current of 5 ampere. If it is placed in a uniform magnetic field of 0.2 Tesla acting perpendicular to the plane of the coil, calculate the torque on the coil when its plane makes an angle 60 degree with the direction of the field. In which orientation will the coil be in stable equilibrium? Again, see, you can see that the questions are lengthy. There are a lot of things, but by looking at the length, you don't need to worry. Don't be tensed. Don't be tense, because this question, is it a tough question? What do you think? Everything is given. They are just asking what is the torque. Torque acting on a current carrying coil. So this question is based on the topic torque on a current carrying coil. What is the formula for torque on a current carrying coil? You know that when a current carrying loop is kept in a magnetic field, it experiences a torque. Uniform magnetic field, it experiences a torque. What is the formula? It is NIAB sin theta. NIAB sin theta. So everything is given. So what are the datas? N is given 200. Area is given 100 centimeter square. It should be converted into meter square. Okay, so 100 into 1 centimeter is, that 10 raised to minus 2. Squaring we get 10 raised to minus 4. So 100 into 10 raised to minus 4, that is equal to 10 raised to minus 2 meter square. This is area. Okay, this is the area. Then what is the current is given? I equal to 5 ampere. Magnetic field B is given as 0.2 Tesla. 0.2 Tesla. Okay, so everything is given. Now what they are asking, calculate the torque on the coil. Its plane makes an angle 60 degree. There is a confusion. There is a confusion. What is that? Tell me, what is theta here? What is theta? It is angle between what? Theta is the angle between magnetic field and area vector. Area vector means cross-sectional area of the coil is like this, means area vector will be like this. So here, if you are taking the magnetic field direction like this is B direction. In this question, it is given that if the plane of the coil is making an angle 60, so I can keep the plane of the coil like this. This is the plane of the coil. The coil I am arranging like this. This angle is given as what? 60 degree. Angle between the plane of the coil and magnetic field. Now if plane of the coil is like this, how can you draw area vector? Area vector is perpendicular to the plane of the coil. So we get area vector like this. That means, please note that this angle is what? Theta. This angle is theta, means that is equal to what? 30 degree. It is not 60. That's the only confusing part in this question about how to take the value of theta. Yes, correct, like Ashmita. Right answer. Tanvi, right answer. Right. So now we can directly substitute. Torque is equal to NIAB sin theta. Directly substitute. N is 200. 200 into, you can tell me the answer also. I is what? 5. Area is 10 raised to minus 2. B is given as 0.2. 0.2 into sin 30. Sin 30, 1 by 2. 1 by 2. So everything would get cancelled, right? So 2 and this 2 will be cancelled. This and this will be cancelled. 5 into 0.2. What is the answer? 1, right? 1 Newton meter. Very good. 1 Newton meter. Smriti, right answer. Yes. Torque is equal to 1. Okay. So once again I am saying, like, don't be tense by seeing a question. You guys are capable. You can do it. Okay. Just see, most of the questions are formula based. So once again, go through all mathematical equations and think each and every term representing what. Okay. So 32. Some more questions are there? I feel a bit tired. Sunil sir, can you?
Sir, actually we are entering to the 4th hour already.
Yes.
We have entered into the 4th hour of life. And thank you for your love and support, everyone. We have just magnetism and like we are in the last part of the magnetism.
I think we can go a bit quickly.
Yeah. Induction and AC, that is what we are going to focus now. Magnetism and matter, we have few questions, and as you know, we have that magnetic properties, sir, so they can just directly revise those concepts. We'll skip some questions from that part quickly because we don't want to keep you for long, like, for this that particular part, because as per the syllabus, we have magnetic properties only from the magnetism and matter part important, right?
That's so just they can go through it.
Yes. So that, I'll give you the analysis. And
tomorrow's session, I think it won't take this much time because only optics will take some time. Rest of the chapter we can simply go through.
Yes. And since we are discussing numerical questions, that takes time. That's time. And also our interaction is also going on.
Yes. Okay, sir,
Anyway,
just carry
but
on.
it's interesting. You keep messaging, you keep commenting answers and all, asking doubts. It's very good. So can I continue with some
Sure, sir,
questions?
sure.
Yes. So as I told you, we will start soon that induction and AC part. Very soon, and we have a surprise visit also. Right, and I'll let him join soon. Before that, we'll finish this magnetism and matter part. Okay, and we'll just analyze the chapter. One or two questions I feel like doing is also there, like a little tricky questions that only we'll mention, and then we'll go to induction and AC, and very soon we can finish. Like around we have 10 maximum 12 questions from induction and AC together. We'll finish it off. Okay, so stay tuned. After that, as I told you, we have to just mention those graphs and devices. Just we'll running through that quickly, just a tour of concepts through that particular part, AC and devices, and we'll wind it up after that. So we won't take much more time. Please be online. Okay. See, question number 33. We'll just try this question. It's a conversion of galvanometer part, I think. An ammeter of resistance 0.8 ohm can measure a current up to 1 ampere. Find the value of shunt resistance required to convert this ammeter to measure a current up to 5 ampere. Second part of that question is conversion of a galvanometer into a voltmeter. I'm coming back to the first part. I feel like doing this question because it is not a direct conversion of galvanometer into ammeter. Just read that question once again. An ammeter, already converted a galvanometer, is an ammeter. It has a resistance of 0.8 ohm. It can measure up to 1 ampere. That is a limit of that particular ammeter. We know when we convert galvanometer into an ammeter, it has a limit, it has a range. It cannot measure beyond this value. Okay, it can measure up to 1 ampere maximum. That is how it is designed. Now what we have to do, we have to connect a shunt resistance to that ammeter. See, galvanometer is converted to ammeter by connecting a shunt. Such a meter has a resistance 0.8 ohm, total resistance 0.8 ohm. It has a limit 1 ampere. Now, connect one more shunt resistance to that particular ammeter so that limit of ammeter should be changed to what? 5 ampere. If so, how much resistance you have to connect as a shunt? What is the value of the shunt is the question. Okay, so it is not a direct conversion of galvanometer into ammeter. We know that conversion equations, right? Shunt resistance equation and all, but that is not required in this case. It is a slightly different approach. See, what did we do before? Like we have a galvanometer. To convert galvanometer into ammeter, we connect a shunt resistance in parallel, right? And we had equations to find the shunt resistance value. This was the range of ammeter I, and the current flowing through the galvanometer was Ig, full deflection current. This current was I minus Ig. So whenever you have confusion in the equation, just remember we equated potential difference of galvanometer and shunt resistance, equated them because they are in parallel, right? So Ig into G is equal to I minus Ig into S, shunt. From that, shunt is equal to I divided by I minus Ig into G. We missed a G here, right? Ig into G. So that is how we found shunt resistance value. But as I told you, the question is slightly different here. Let us check what actually happens. We have a galvanometer converted ammeter, correct? Galvanometer converted ammeter. What is its resistance altogether? We have the resistance given 0.8 ampere, 0.8 ohm, and limit of this ammeter is found to be 1 ampere, which means only 1 ampere, up to 1 ampere current this ammeter can measure. You can send only up to 1 ampere current through that ammeter. Okay, so that is the ammeter given here. You have to convert this ammeter by connecting one more shunt resistance, okay, so that range should be converted to 5 ampere. So let me connect a shunt resistance in parallel, and let me take it as some S is a shunt resistance, so that you can send a current up to 5 ampere, right? Up to 5 ampere. Limit of that ammeter is going to be 5 ampere. I hope you got the diagram. If the diagram is clear, problem solved, right? We already solved this problem. See here, I told you the given ammeter has a resistance 0.8 ohm. It has a limit of 1 ampere. That is why I marked 1 ampere here. Only 1 ampere current, up to 1 ampere current maximum, can be sent through that ammeter. So what happens when you send 5 ampere through that particular ammeter? The rest 4 ampere should flow through what? That shunt resistance, right? Because 5 ampere we send into this, and this ammeter can take only 1 ampere. The rest 4 ampere should flow through shunt resistance. Done. Finished. Now we can say the potential difference is equal. Correct? We can say 1 ampere into 0.8 is equal to 4 ampere into S, because that ammeter and the newly connected shunt resistance are in parallel. What is current flowing through ammeter? Maximum of 1 ampere, right? Then remaining 4 will be flowing through shunt resistance in parallel. Yes, so potential difference across this ammeter and potential difference across the shunt resistance will be same because they are parallel to each other. Find out S. See, very easy. 0.8 divided by 4. So that is a value of shunt resistance to be connected in parallel, which is 0.2 ohm. Okay, 0.2 ohm. So that question was a slightly twisted one, not direct conversion of galvanometer into ammeter. That is why I felt like doing that question. Okay, so I hope it is clear. Yes, Venkata, Hashmita, Salman. Yes, many of you already solved that already. It is 0.2 ohm. Okay, so in very easily we solved that question. So for that, you should know exactly what is ammeter, how it is converted. Okay, what is the meaning of maximum current? What is the meaning of range of ammeter, right? So if you say it has a range 1 ampere, it can withstand only up to 1 ampere current. If you send more current through it, that device will be damaged, right? Yes. So that was the first part. Second part I am not going to do. I'll just give you the equation because it is direct substitution of that conversion, galvanometer into a voltmeter. We know how did we converted galvanometer into a voltmeter. That was a series combination, right? This series connection of a high resistance and this has a resistance G. Then the whole device is now called a voltmeter, where this is the potential drop 1 and this is the potential drop 2, V2. The current flowing through this will be IG, galvanometer current, we know. There is no branching of current, there is no division of current because there is no more branches, one single connection, series combination. Yes. So that potential V equals to V1 plus V2, which is IG into capital G, sorry, plus V2. V2 is going to be IG into R. See, I'm just telling you to derive that equation because it may be confusing. In 2 steps, we got the equation for shunt resistance, right? In 2 steps, we will get expression for what? R also. Correct? So we can say V minus, we can take IG here, V minus IG into G. Okay, so we can say V minus IG into G is equal to IG into R. Therefore, R is equal to V by IG minus capital G, right? This is the value. And look at the question. See, this equation, if you remember, start from there. Okay, if you are confused, remember how did we derive it in 2 steps. In 2-3 seconds, you can derive that equation. No mistakes. Okay, so look at this. You are given, we are asked to calculate what is R. V is the range of voltmeter. I think it is 3 volt in the question. Right, let us check. So we can go to the question. Range of the voltmeter is going to be 3 volt, right? It's given. Full scale deflection is given as 4 milliampere. That is your IG. IG is 4 milliampere. Fine. And what is the next quantity given? 16 ohm is the galvanometer resistance, which is capital G. See, look at that. All values are given. V is given, IG is given, capital G is given. Just substitute and simplify. It's up to you, right? But the previous question was slightly twisted. Fine. Then moving on to the next one, question number 34. It is, yeah, exactly. Venkat, that answer you have to cross check because you missed some conversion, I think, milliampere. There is a milliampere, that's a very common mistake we commit. IG is 4 milliampere. 4 milliampere should be converted to 4 into 10 raised to minus 3 ampere, okay? Then your answer will be different. Yes, yeah, be careful. Now, yes, question number 34 is a closely wound solenoid of 2000 turns and cross-sectional area 1.6 into 10 raised to minus 4 meters square carrying a current of 4 ampere is suspended through its center, allowing it to turn in a horizontal plane. Yes, we have 2 questions. Magnetic moment associated with the solenoid, that is question number 1. Question number 2, to find the torque acting on the solenoid of a horizontal magnetic field. Okay, so magnetic field strength is given, torque is to be calculated. Question is based on the concept that a current carrying solenoid is equivalent to a bar magnet, right? Yes. We know they are very similar. A current carrying solenoid produces a magnetic field equivalent to a bar magnet, right? Both of them behaves in the same way, we know. We have, if this is a dipole, if the bar magnet is a dipole, this is also a dipole. What dipole? Magnetic dipole, right? Equal and opposite poles separated by some small distance. Okay, so the question is based on that concept. Let me give you some hints to solve this. See, in this case, solenoid has 12,000 turns. Cross-sectional area is given in meter square only, so nothing to be worried about the conversion or nothing. So it's directly given in SI unit. Current is given, and we know any current carrying loop or solenoid can have a magnetic dipole moment, which is given by NIA, right? NIA, that is the equation. We know magnetic dipole moment is there for bar magnet, because bar magnet is a magnetic dipole only. And also a current carrying loop of wire, correct? Because that behaves like a magnetic dipole. And if you have so many loop of wire connected, that is called a solenoid. So solenoid also has magnetic dipole moment. And luckily we have given all the values. Capital N is 2000. I is what? I is 4 ampere. A is the cross-sectional area. You just substitute, multiply, simplify. That will be your value. And unit is ampere meter square, right? That is your magnetic dipole moment. Okay, first part you just go through, okay? Fine. Because it is direct substitution, all values were given, nothing else. Now, second part of the question, the torque on the solenoid, if horizontal magnetic field of 7.5 into 10 raised to minus 2 is set up at an angle of 30 degree with the axis of the solenoid. See, that is like just the matter of understanding what is the situation. See, this is a solenoid, for example. Yes, and solenoid has an axis. Axis in the sense, the line passing through its center. Fine. We apply some magnetic field here. Uniform magnetic field. That uniform magnetic field B makes an angle, how much? 30 degree with the direction of dipole moment. Direction of dipole moment of the given dipole. Okay. We know what is the torque acting on a dipole. That also a direct calculation now. Torque is equal to mb sine theta, right? I told you the equation already. Yes, exactly, Ashmita. That is the answer for that conversion question, right? You completed that. Very good. Then, yes, keep going. Torque is equal to mb sine theta. That was the equation for torque. And here also we have all the values given. Magnetic dipole moment will be the value you have calculated here that you have to use in this. You can substitute here. B, what is B? B is the magnetic field strength that was given, 7.5 into 10 raised to minus 2 Tesla, value given in the question directly. And sine theta, theta is given as 30 degree and sine theta is going to be 1 by 2, correct? All values are given, direct substitution only. So read the question properly. If you just remember the equation, some of the question can be very easily solved by directly substituting and simplifying it. Okay, 2015 paper. Okay, fine. So that was question number 34. And 35 is an alpha particle question, like, it is entering to a magnetic field. This also, don't be scared by looking into this values given. And when you substitute also, we get something in the square root, which can be easily simplified. I'll quickly run through it. Hope you remember what happens when a charged particle accelerated through potential difference 10 kilovolt. It is an alpha particle. Yes, moves along x-axis. It enters in a region of uniform magnetic field B 2 into 10 raised to minus 3 Tesla acting along y-axis. So alpha particle was moving along x-axis and magnetic field is directed along y-axis. We know this is the theta is equal to 90 degree case, right? Yes, when the charged particle enters normal to the magnetic field, we know, what do we know? It undergoes a circular path, right? Yes, it undergoes a circular path. The question is, find the radius of that path. The only thing you have to be careful here, choose the right equation. That's it. we have a different form of the same equation. R is equal to mv by qb was the very basic form of that equation. M is the mass, v is the speed, and q charge, b is the magnetic field, right? Okay. Look at this question. You are given some other values. One, it is mass of alpha particle is given. Mass. Okay, mass of alpha particle is given, that can be used. But speed is not given, right? Instead, you are given kinetic energy. Yes. Right? Not kinetic energy, potential difference. It is accelerated through a potential difference, so it gained kinetic energy. So the same equation, we had some other form. mv is momentum, so R is equal to P by QB, in which momentum can be related to kinetic energy as 2me divided by QB. And that kinetic energy E can be written as Q into V, right? Where V is the accelerating potential. Weight, that is what given in the question. Accelerating potential. So we have to go for that equation. R is equal to root of 2 times mass of alpha particle into charge of alpha particle into accelerating potential, the whole divided by QB. Now look at this equation. You can see 2 is a numerical constant. M is mass of alpha particle, which is given in the question as 6.4 into 10 raised to minus 27. Q is charge of alpha particle, and for your information, we know that charge of alpha particle is 2e, right? Yes, so Q is going to be 2 into 1.6 into 10 raised to minus 19 coulomb, right? That is charge of alpha particle. Yes. Okay, so we have that value also. Q. V is 10 kilovolt. Remember, 10 into 10 raised to 3 volt. Okay, that should be the substitution. And B is given as 2 into 10 raised to minus 3. So direct substitution. Don't be scared of the square root. You will get a perfect square in this square root. Okay. On simplifying, you will get R is equal to 10 meters. You just try. That calculation is really interesting because all these quantities are going to be ended up with a perfect square, and you can take the square root easily. Okay, so selecting the proper equation is the first part of your solution. If you do that, then the rest is easy. Calculation is given. The given numerical values are adjusted accordingly to get a proper easy calculation. Yes. Okay, so you try this. Q is equal, yes, Zabi, and that was a torque, right, Venkat? Come on, fine. That was the end of that magnetism part, like moving charges, and we have some long answer questions given here, which might be like mentioned before. Expression for force acting on a moving charge, right? And under what condition it follows circular path and helical path. As just I mentioned before, if you want to get a circular path, charge should enter perpendicular to the field. Theta is equal to 90. And for helical path, theta should not be 0, 180 or 90. Any other angle is fine, right? F is equal to MQB sine theta equation. That part is asked for like in 2017 paper. Biot-Savart law vector form is asked to be represented here. And it is a 2-mark question. It's a part of 2-mark question. So just the vector form of that Biot-Savart law representation. It's a conceptual one again. And this is the most important derivation. I would say that you should revise from this. Like derive expression for magnetic field on the axis of a current carrying loop, application of Biot-Savart law. That equation that you hope you can identify from the diagram, right? So we have something like this to derive, and we get B is equal to mu naught I a square divided by 2 a square plus r square the whole raised to 3 by 2, which can be simplified into mu naught I by 2a for field at the center, that particular derivation. And I would say this is the most important derivation you have to remember from this chapter, okay? And followed by 2 long straight conductors, that force between 2 parallel conductors. You have done one numerical question from that part, right? Sorry. And hence define 1 ampere. And that question is very important, okay? Whenever we get that derivation, F is equal to mu naught I1 I2 divided by 2 pi r into L. This was the equation, right? Using this, we have to define 1 ampere. So how did we define that 1 ampere? We have taken so we have taken this force to be calculated, taking I1 is equal to 1, I2 is equal to 1, R is equal to 1, L is equal to 1. So we get mu naught, that is 2 into 10 raised to minus 7 will be the force. So by using that, we just explained what is that, what is 1 ampere. That is how what we have to define from this. Okay, so remember that particular derivation also, force between two parallel conductors, followed by working on principle of moving coil galvanometer, one of the repeating 3-mark question, construction, principle and working. Yes, fine. So followed by this, in that particular unit, we have magnetism and matter. Okay, and I'm not going to discuss questions from that part because, as I told you just in the beginning, that is the magnetic properties of materials. That particular part you make perfect. We expect questions mostly from that particular part. Look at this. Third topic is magnetic properties of materials. Most of the questions we get from that particular part. Okay, so we expect this year also questions coming from that part. So make that table, you know, the properties, examples of diapara, magnet, materials. Just make sure you're okay with those concepts. And this is to identify magnetic material by looking into the susceptibility. We know what is the susceptibility range of dia, para and ferro, right? So we don't have to waste time on these kind of questions. We know how to identify these materials. Okay, so we don't have much difficult questions from this part. So I hope moving in magnetism and matter part for you, it is under control. And we have to go to the last part of this discussion, that is EMI and AC. We have just around 10 questions more to complete. So hope that will be fine. Yes, and yes, next one is electromagnetic induction. So 4 or 5 questions from induction and 4 or 5 questions from AC also. We'll go through that quickly. Okay, and this is one of the very important portion. So we have loads of derivations and also coming from AC also, right? So long answer questions, and also AC is a little confusing too. Stay with us. So Mr. Ali Fasil sir will come and continue with the next part, like induction and AC. Just 10 more questions we have to go for. Stay online, okay? And we'll be coming together to the last part. Until then, bye. Okay, one more thing. See, as I told you that graph questions, device questions will be just coming up with, we come all together with that particular questions. Okay, just we will take around 10-15 minutes, that's it. Then, yes sir, over to you.
Yeah. Thank you, sir. Hi, hello all, my dears. How are you? Okay, you are almost on the 4th hour of the today's live session. Hope you are enjoying the sessions. The last final lab we are doing. Okay, so almost the first volume chapters we done. Last 2 chapters we have EMI and AC. Most easiest one you feel. Okay, most important questions we'll be doing. Okay, Azim is there, Smriti, yeah, all Atul is there. Yeah, great. So let's go. The last moment. So I'll be giving the tips and most probable questions. Okay, so stay tuned. See here, if you go to electromagnetic induction, EMI, these are the main analysis of the last 10 years questions. See here, the most important area is coming from this one, the 6th point, nothing but the inductance. EMI, the inductance, both self-inductance and mutual inductance, both important questions. You know, the most probable question from this chapter is to derive the mutual inductance and to derive the self-inductance and the problem in between. Okay, so let's go through this one. Then probable items are there. Okay, the motional electromagnetic EMF, the force is there, one idea. Then we have Lenz's law and conservation of energy. Few areas are there. Okay, most of the long answer questions came from the inductance only. So please focus on more on that. I hope all of you already prepared it well. So let's go for some previous year questions directly. Here is the questions. What is the direction of induced currents in metal rings 1 and 2 when current I in the wire is increasing steadily? See, current is going from this one to. Then what is the direction of this one? You might be seeing any question paper you see, this type of one question will be there. Okay, so there Lenz's rule you have to apply and the Faraday's laws of electromagnetic induction, of course you know. So here see, so right hand thumb rule you have to use to get the direction of magnetic field. In which direction magnetic field is increasing, to the opposite direction will be the current. Is it? Lenz's rule says the induced current is in such a way that it opposes the change in the cause. Is it? Yeah, always is there. Yeah, Smriti, yeah, great. Ashmita, yes, great. See, so it's going right on. See on the first coil, it is on right side. First coil is upward. So you can see If you use the right hand thumb rule, the fingers are outward. So at the first finger, the first loop, the magnetic field is outward, perpendicularly out of the plane of the board. Clear? That's very important. Now it's increasing in outward. So an increasing magnetic field, it should be opposed by this face, so that it should be a clockwise. You might remember we used to write a clockwise like this way. Is it south pole? And decreasing one, if you take it away like that, so it's opposite like that, it should be north pole. So the upper surface and lower surface, that you have to think it. So here see, what is the direction of induced current in the metal rings 1 and 2 when current is in. So in first case, what is your idea? Yeah, great. Ashmita, great. One is clockwise and 2 will be the same way. If you do, here see, right hand, it is into the board. For the second ring, into the board is there. So it will be anti-clockwise. Great. So anti-clockwise, right what? And north pole it should be. Anti-clockwise. Fine? Okay, yeah, great. Almost get it. Good. Tanvi, you got it now. Great. We'll go to the next one. Okay? Second question. A horizontal conducting rod 10 meter long, extending from east to west, is falling with a speed of 5 meters per second at right angles to the horizontal component of the Earth's magnetic field. BH is given 0.3 into 10 raised to minus 4 Weber per meter square. Find the instantaneous value of EMF. See, 2017 question it is very simple and direct. 2 mark question it is. It is regarding the motional EMF. All of you know, motional EMF E is equal to BLV. The equation we have, is it? So BLV we have. Direct. B is given, L is given, V is given. Is it? So this is B. Is given 0.3 into 10 raised to minus 4. Then L, length is given 10 meters. Speed V is given 5 meter per second. Simple. BLV, just multiply only. Okay. For lack of time, just we are keeping the tips. Please note down it. You have to solve it in detail. Okay. Just mere multiplication only. No conversion is required because all are in SI units. 10 meter is there. 5 meter per second is there. 0.3 into 10 raised to minus 4 Weber per meter square is there. Hope you got it. Is that fine? Yeah, great. Smriti got the answer. Ashmita is there. Great. Okay. I'm going to the next question then. So motional EMF, another point. EMF will be BLV, the magnetic field into length into this velocity speed. Okay. There one derivation also is there. I hope you might be practiced already. From Faraday's law, we can get the motional EMF. If a rod is moving perpendicularly in a magnetic field, how much EMF is induced? Hence current also we can find out. Is it? Fine. Yeah, Venkata, good, great. So we'll go to the next question. 41st question. It's 2016 question actually. One problem, most area. Define mutual inductance. To define mutual inductance, many equations you can use it because wherever mutual inductance comes, that equation you can use it. Mutual inductance, one simple equation is there. What is it? The flux associated with one coil, phi 1, 2 is equal to M12 into I1 you can say. Flux linked to the nearby coil is equal to mutual inductance of the coil between and current in the first coil, is it? So M12 is the, you can say M12 is phi 12 by I1. When unit current passing through the primary coil, then flux induced or flux linked with the secondary coil is called the mutual inductance. Simple idea. Or you can have another equation. EMF E is equal to M into di by dt. Then there also you can have M is equal to E by di by dt. The mutual inductance is the EMF induced in a coil when there is unit rate of change of current in the nearby primary coil. Like that, from the equations you can derive it. Define it. Okay, fine. Next question. This is part 2. A pair of adjacent coils have a mutual inductance of 1.5 Henry is given. If the current in one coil changes from 0 to 20 ampere in 0.5 seconds, what is the change of flux linkage with the other coil? Change of flux linkage, see this equation directly can use it. Mutual inductance is given, then current change and time is given. So we know that E is equal to d phi by dt. That is equal to m into di by dt. Is it? EMF in Faraday's law, d phi by dt we have. That's equal to m into di by dt. Is it? So if you use it, you want to find the change of flux linkage with the other coil. So d phi is equal to m into di. So change in flux, mutual inductance into change in current. Mutual inductance is given, then change in current is given from 0 to 20, so 20 ampere. Just multiply, you get d phi. Is it fine? Okay, so change in flux is asked. So EMF have two equations we have, d phi by dt and m di by dt. Just equate both, you will get the change in flux. Hope you got it. Yeah, great. Sinan got the answer. Yuvraj. Yeah, Mohammed. Fine, great. Clear. So for timing, I'm just keeping the calculation part. Sorry for that. We'll be going to the next question. Okay, while you watching this later also, pause the video and solve. Okay, let's go to the next question. A circular coil of cross-sectional area 200 centimeter square and 20 turns is rotated about the vertical diameter with angular speed of 50 radian per second. So angular speed is given in a uniform magnetic field of magnitude 3 into 10 raised to minus 2 Tesla. So it is rotated in this one. Calculate the maximum value of current in the coil. Maximum value of current you have to find out. So actually is a theoretical question regarding AC generator. Is it? In AC generator, you know, between the magnetic poles, we rotate the coil and EMF is induced. And the maximum current, you might be remembering it, I0 is equal to NBA omega. You remember it? You have I is equal to I0 sin omega t, that I0 will be NBA omega. Is it? Yeah, Yuvraj, remember it? Yeah, get it. So I0 is NBA omega. N, number of turns given. B, magnetic field. A, area of cross section. Omega, the angular frequency. Everything is given. You have to find the maximum value of current. Is that fine? Yes, great. Venkat got it? Yeah, Smriti, fine. NB omega. That question only. Please substitute and multiply it. May I go for the next? Yeah, great. I'm sorry, that is E0 actually, then I0 will be, this by R will be. So that resistance is mentioned, no? Wait. I is equal to E0 by R should be there. Okay. E0 is 0, I'm sorry. Yeah, that's great. Then I0 will be, after this E0 by R should be. So NB omega by R will be. Okay. Fine, great. So to substitute that one. Okay, then we ready. The next question we are checking. Two coils C1 and C2 are placed close to each other. So nearby they are kept. The magnetic flux phi2 linked with the coil C2 varies with the current I1 flowing in coil C1 as shown in the figure. So phi2 versus current is given in a graph. Okay. Find the mutual inductance of the arrangement. What is the mutual inductance of the arrangement you have to find? And the rate of change of current that will induce an EMF of 100 volts in coil C2. Two questions are there. Say graph is given, phi and I. Mutual inductance you have to find out. Is it? So fine. See, you have mutual phi equation. We have phi is equal to m into I. Most simplest form I am writing. Okay, 1, 2 should be there. Then m will be what? Phi by I. Is it? So here phi is along y-axis, I along x-axis. So current in primary coil x-axis, flux in secondary coil in y-axis. So if you find the slope of the graph, you'll be getting this one. Is it? Phi by I. So just find the slope. So it is 15 by 6. It's fine. So it'll be, yeah, great, 2.5. Is it? That's a mutual inductance M. Now, the rate of change of current that will induce an EMF of 100 volts in coil C2. So just now we got it. EMF E is equal to M into di by dt. You have to find the di by dt here. So di by dt will be equal to E by M. EMF is given 100 volt. M you will get from here. Substitute. So E by M also you will get. Is that clear? Yes. Yeah, 40 will be the answer. Simple. So here, phi M into I. M is phi by I. Normal equation. Then phi 2. Suppose you want to find mutual inductance of second coil with respect to first. Then phi 2 by I1. Mutual inductance of first coil with respect to second. Then phi 1 by I2. That's all. So here phi 2 and I1 is given. That's all you have to find out. Okay, fine. dA by dt by E by M. It's clear. Please substitute the values and you solve it. Yes, Venkata. The next one. When a conducting loop of resistance 10 ohm and area 10 centimeter square is removed from an external magnetic field acting normally, the variation of induced current in the loop with time is as shown in the figure. So current changing with respect to time is given in the graph. So it is removed from a magnetic field. So there is a change in magnetic flux. There will be induced current will be there. So that change is given there. Fine. The total charge passing through the loop. Charge you have to find out. Then 2. Change in magnetic flux through the loop. Change in magnetic flux. d phi by dt you have to find out. 3. Magnitude of the magnetic field applied. B you have to find out. So 3 items. That question says, first of all, total charge passed through the loop. Charge means, Q is equal to I into T, I into T. Here I is along y-axis, T is along x-axis. So if in a graph, y-axis into x-axis comes, you have to find the area of the graph. So just find the area of this one. It's a triangle. So here be area of the graph. Okay, fine. Area will be how much? Half into base into height, 1 into 0.4. So that will be fine. Yes, will be 0.2 will be. Then that much coulomb. That's the charge passing through this one. Next, change in magnetic flux through the loop. Change in magnetic flux, that is d phi by dt you have to find out. Okay, so how will you find d phi by dt? We have EMF equation. So d phi by dt. For that purpose, we have given the area of cross section is given 10 centimeter square. Okay, and flux we have phi is equal to B into A. Flux is phi is equal to B into A. Is it? Then we have to find the change in flux actually. So d phi by dt. D phi by dt will be equal to, we have d by dt of B into A. So area is constant here, 10 centimeter square is there, then dB by dt. So that will be A into dB by dt. Now also d phi by dt we have E into, that E is equal to d phi by dt, So that can be used here for this equation like di by dt. If you use di by dt, then we have E is equal to. So n di by dt can use it phi. So it will be how much almost? Change in magnetic flux will be, this equation also you can use here, dA by dt. Yes, Kavisha, you are using. Two is anticlockwise, but this is Kavisha, you are the previous question you are asking. Okay, let's be. So here, see, so total charge passed through. Q, we got it. Change in magnetic flux, d phi by dt. Then magnitude of the magnetic field, B also you can find. So for that, B will be equal to, you can just rearrange this one, d phi by dt by A will be. So after getting di by dt by A if you do, you will get B also. So relation, mutual induction, then rate of change of flux, rate of change of current, B you multiply it. That three equations you are equal. Is that okay? Yes, Tanvi. Then next question let's do. Yeah, few conceptual and long answer type questions which is we are not included in the direct sense. State lenses law. Statement you should keep in mind. Okay, because here and there that question is repeated. Then Here, Lenz's law is a consequence of the principle of conservation of energy. Is also you have to justify the statement. One question. Then, magnetic rod of length L is rotated with frequency. One solved question is there in the NCERT book. Half I omega square, that omega square equation, L omega square equation is there, that will keep it. Yes, fine. Okay. Define mutual inductance between a pair of coils. There are expression for the mutual inductance. I already told you in the between. Inductance is the most probable area of this chapter. So, self-inductance or mutual inductance to find. Is it? Fine. Okay. Then we have basic principle of working of AC generator. You should do it. Direct questions is all. Yeah. Next is alternating current. The last part of this today's discussion. Okay. Hope you are there active. Please be there. We'll be doing in short time. Okay. I'll give the tips for the questions. AC, if you go through alternating current. See, most important part is the fourth part. Fourth part is nothing but the series LCR circuit. Series LCR circuit, most important part of this chapter. AC. Okay. Few more questions we have. So please stay tuned. Be energetic. We'll be doing it. Okay. See the question number. A resistor of 30 ohm and a capacitor of 250 by pi microfarad are connected in series to a 200 volt 50 hertz AC source. Calculate the current in the circuit, the voltage drop across the resistor and the capacitor. Then, is the algebraic sum of these voltages more than source voltage? So, two concepts are there. First of all, current in the circuit. It's very simple. You know, current I will be equal to V by Z you have to do. The impedance or the net resistance of the circuit. What is net resistance? Here actually, one resistor is there and one capacitor is there. There is no inductor. So, we can have, it will be V equal to root of R square plus XC square. You remember the impedance equation. Root of total LCR we have root of R square plus XL minus XC the whole square. Here R square plus XC square is there. Okay. Now how will you find XC? XC is equal to 1 by C omega. Substitute C is given. So F is given frequency 50 hertz. So if you substitute XC you will get R square plus XC square you have to do. Then V voltage is equal to 200 volt. Okay. Actually these numbers 30 ohm 30 square plus XC will be almost 40 ohm. If you divide it, 40 will be there. So this root will come 30 square plus 40 square. That is equal to 50. So 100 will be almost 3/4. So that 200 you have to cancel. Got it? Yes, I am giving the tips. So please note. I is equal to V by Z. Then how to find Z and all. Current you will get. Then voltage drop across the resistor and capacitor. That's very easy. Voltage V is equal to, you know, I into R across resistance and across capacitor I into XC. I into XC. Is it? Just after getting this one, you have to multiply here. Voltage drop across resistor and capacitor separately. Okay, hope you will be doing it. Please note the tips. You have to keep it. Then third one. Is the algebraic sum of these voltages more than the source voltage? So algebraic sum means just you have to add up both. Definitely will be more than. But you know, in RC graph, if you do it, actually VR will be along, if x-axis is there, then you know VC will be, there will be. So both will be perpendicular to each other, VR and VC. Because if I is along this one, then will be lagging behind. Then resultant will be, you have to square it. So resultant voltage will be V is equal to root of VC square plus VR square you have to do. So that definitely will be the resultant voltage, not the algebraic sum. That you have to prove here. Solve the paradox. Direct addition won't give you answer. So root of this one, you have to take it. So come on, current, how to find? V by Z. Voltage across each one. Then total voltage will be root of VC square plus VR square. Please note the tips, we'll be doing it. Okay. Fine. So next question I'm going to. A device X is connected to an AC source V is equal to V0 sin omega t. The variation of voltage, current and power in one cycle is shown in the following graph. So since V is given V0 sin omega t, voltage is a function of sine. Sine 0 is 0, you know. So at 0, which graph have 0 value? So both A and B have the 0 values here. So either A or B is voltage. Next check, when sine is pi by 2, this is pi by 2 value. Sin pi by 2 1. So V will be maximum. So here is the maximum value. So B gives you the voltage. Definitely done. Then if V is voltage, with that the dotted one is leading. So C will be the current. And A is giving the half cycles. So A will be for power. You identify the device X. Current is leading the voltage. Current is leading the voltage. That will be capacitor. Yes, great. So it will be a capacitor. Then, justify your answer means you have to give the equations and all. How does its impedance vary with the frequency of the AC source? XC and XL. XC graph we have with omega. So X is 1 by C omega. As omega increases, it will be decreasing. XC. Then obtain an expression for the current in the circuit and its phase relation with the AC voltage. You remember that equation derivation? I is equal to I0 sine omega t plus phi. You have to derive it by using QC. That equation. Q is equal to C into V. So dq by dt, if you differentiate it, that derivation you have to keep in mind. Okay. So for time is, I'm just adjusting the time. So this one, you have to do it. It's clear. Hope you got it. Yeah, Bangada got capacitor. Sure. Smriti, great. Okay. The next question then. A resistor R and an inductor L are connected in series to a source V is equal to V0 sin omega t. Find the peak value of the voltage drop across R and across L. Peak value of the voltage V0 you have to find out. Phase difference between the applied voltage and current. Which of them is ahead? So across R and L you have to find out. That's all. So there across R means the Z will be equal to root of R square plus XL square equation. XL square. Z you have to derive. So phasor diagram you have to draw and find this one. Just sub cases of LCR series this one. Here only R and L is there. Previous circuit we have R and C we done. Here R and L only. Okay. Then phase difference phi to find out. You know phi will be what? Phi is equal to how much will be? Between R and XL. Phi will be. So here phasor diagram. This is VR and this is VL. So angle between this resultant will be this way. So this is phi, you do it. Then phi is equal to tan inverse XL by R will be. Opposite by adjacent. XL by R. So that derivation you have to show here. That's only. Numerical values are not given. So do it. Clear phasor diagram method, you can use it. Okay. Yes, tan phi formula. XL by R. Tan inverse XL by R. Clear? From the phasor diagram only, Smriti. Yes. Okay, so I'm going to the next question. A 2 microfarad capacitor, 100 ohm resistor and 8 Henry inductor are connected in series with an AC source. So it's LCR, capacitor, resistor and inductor. What should be the frequency of the source such that the current drawn in the circuit is maximum? If current become maximum, then you know that case is called a resonance circuit. Is it? Fine. What is this frequency called? Resonance frequency it is called. Then what should be the frequency you have to find out? So you know F is equal to 1 by 2 pi into root of LC. That is frequency. Just frequency ask it. Or omega angular frequency you can get it. 1 by root LC. So 1 by 2 pi LC. L is given inductor. C is given capacitance. Multiply and substitute, you get the frequency. Then, if the peak value of EMF of the source is 200 volt, find the maximum current at resonance. You know, at resonance we have Z is equal to R. Impedance will be the minimum, least one. So that I0 will be equal to V0 by R only, peak value. So R is 200 volt is given peak value. So R is given how much? 100 ohm. So 200 by 100. Fine. Peak value also got it. That's the second one. Then draw a graph showing the variation of amplitude of the circuit current with changing frequency of applied voltage in a series LCR circuit. So we have that graph, omega here and I0 here. See a peak value. Is it? Then that's for R1 you can say, for example. Then as R1 increases, I0 will decrease. So R2 is given here. Sorry, R1 is greater than R2 is given. So R2 is smaller. Then will go higher. then peak will be there. So this is for R2. This graph is given in the NCERT book also. This will be the graph, variation. Okay, great, yes. Venkata is there, mouse is there, yeah. Tanvi, yes, resonance curve it is. Great, great, great. Okay, yes, I'm going to the next one. 49th question. We have the second last question of this topic. Calculate the value of the additional capacitor, which may be joined suitably to the capacitor C. That would make the power factor of the circuit unity. Power factor is a question. You know power factor, we have equation, power factor cos phi is equal to 1 is given. So phi is equal to how much? 0 degree. Is it? Phi is 0 degree. Cos power factor 1 means phi will be 0 degree here. Fine. Then tan phi is also 0. Phi is 0, so tan phi is also 0. Cos phi is 1 and tan phi is equal to 0 here. Now, you have to find the additional capacitor which may be joined. So, if power factor is unity means this will be LCR is there. So, this is resonance circuit it is. At resonance, you know, XL equal to XC. Both will be equal. Now, XL means what? L is given and omega you can have it, L omega. So, XC is equal to L omega. If you multiply this one, L is 100 millihenry into 1000 is there, that will be 100 only. Is it? Milli, 10 to the minus 3 into 10 to the 3 cos. So 100 ohm is XL. Then XC, you have to find C. So from this one, you get 1 by C omega is equal to 100. So C is equal to 1 by 100 into omega. Omega is 1000. If you do, you will get C. So C will be almost equal to 10, you will get 10 microfarad you will get. But here see, total C is only 2 microfarad. So one additional 8 microfarad you should connect across it as parallel. So it will be total 10 microfarad. So that's the question there. So from equation, XC value got it by comparing to XL. Then from XC we got C. That C, 10 is there, only 2 is available here. So we just connected parallel. So 2 plus 8 will be 10. So 8 microfarad is the additional you should add. Yeah? Yeah, Zabi, fine. Great. Okay, Kavi. Yes. The last question of the session. The primary coil of an ideal step-up transformer is from step-up transformer. Has 100 turns and transformation ratio is also 100. You know transformation ratio, R is equal to NS by NP. The transformation ratio. That's given 100. The input voltage and power are respectively 220 volt, 1100 watts. Calculate number of turns in secondary. NS is equal to NP into 100. NS is equal to NP into 100. Transformation ratio is given. So 100 turns is given. Okay, primary NP. Multiply it, you get the first one. Then current in primary. We have current I is equal to, we have power P is equal to V into I. So primary VP IP. So it give IP is equal to power in input by VP. Is given input 220 volt is there. This is the power. IP will get. Then voltage across secondary VS. We have VS by VP is equal to NS by NP. So VS you'll get. Compare this. Then current in secondary IS. Same case. VS by VP after getting is equal to IP by IS. Cross multiply it. Then power in secondary. Power in secondary will be power secondary is equal to VS into IS in secondary. All direct questions only. So after getting R is given, NS you can get. After getting NS, you can find NS by NP, that is VS by VP. Okay, it's fine. Hope these equations are okay, fine. Step up transformer also one of the important topic in numerical question you can expect it. So here, LCR series circuit, most important, capacitive circuit, inductive circuit. Okay. Then numerical purpose also be done, including transformers. Okay, dears? So this is the last question of this session. Hope all of you done it. Okay, sir.
Yes, good evening.
Yeah.
Thank you very much for this, sir. It's already like 4 hours and 10 minutes.
Almost.
And we can see that some
Yeah.
students were there from the beginning till this. Hope you guys enjoyed. It's not something which we need to enjoy, but I hope you guys got an idea about all the questions from part 1. So we have some more 10 more minutes. We'll be winding up today's session. In that 10 minutes, we'll be discussing circuit diagrams and how to study. Tomorrow also we'll be having the class from 5 o'clock. Main topic is only optics. So
Yeah, optics is my major
try
topic.
to wind it up tomorrow session within 3 hours. That's what our plan. Optics is the main area. Modern physics and semiconductor part we can easily go through. There is number of questions will be comparatively less. Sir, ready?
Yeah, that thing is ready.
Okay, so
So
just
proceed, sir. It's fine. Oh, anything is okay. See, the thing is that we get repeating the graph questions, right? So we are trying to just club all those graphs together so that we can easily identify which graph is for what, and the relation between different quantities. Yes, you stay there, sir. We can go together. Fine. You also come, sir. Join, sir, please. So we are just winding up in 10 minutes, guys. We won't take much more time. It's just from these chapters, the whole graph and devices that you have to concentrate, right, sir?
Yeah, sure.
So only those part we are going to revise once again. Quickly, we'll go through the questions. See, look at the graph. You can see the first one.
Electric field due to infinity long straight car.
Yes.
From Gauss law first application. Is it?
Exactly.
Is inversely proportional to R.
Yes. So what was the relation, sir? E is proportional to 1 by R, right?
Yeah.
Power is 1 only.
Yeah.
See, electric field relation, we have different relations, like for point charge, it was 1 by R square, right? When we come to long straight conductor, it is 1 by R. When it is dipole, E axial and E equatorial, it is going to be 1 by R cube, right?
Yes.
So these different relations we have. So this is for straight conductor, E proportional to 1 by R graph. Okay, that is what we can see on the board.
So inversely proportional relation comes, this is the shape.
Yes.
That's what you have to remember. Okay.
So let us try another one. This is the electric field due to a uniformly charged thin spherical shell. Yes.
Thin spherical shell, inside the shell you know that the field is 0.
Exactly.
So that's why from here and till here, this
Graph
point
is
is
missing.
actually the radius, I mean surface point.
Yes.
So the graph should start from here. On the surface will be maximum.
And this is
after
the
that it is decreasing.
field on the surface, right, sir?
Yes.
So once you come out of the surface, it decreases. Yeah. Okay, exactly. So then,
That's inversely proportional. So, yeah, sir.
okay, fine. Yes.
Okay. So next.
Next graph is like from electrostatics. Once again, look at this.
Plane
See
sheet.
the next source of electric field. It is a plane sheet. We know E is proportional to R raised to what? Raised to what? R raised to?
R raised to.
R raised to?
Does it depend on R?
Yes. No,
Tell
it is
me,
independent
guys.
of R. So E raised to 0, right?
Is a constant throughout the
So it is independent of the distance.
It is independent of
We
the
are talking about infinitely long charge
And
sheet.
this one is a probable MCQ also.
Yes, yeah,
E
relation,
due to
exactly.
How it is related to R. There may be options like R raised R square in 1 by R square.
Exactly.
As the D option, they may give R raised to 0. So
So it is independent of R, right? So it's a uniform field. E remains constant. Yes. Fine.
yes. Next.
Then, sorry, spherical shell, non-conducting and conducting. So this part is not that important anyway, right, sir?
It's not
so
there,
this is
actually,
okay.
but
So this is not required. This one regarding the electric field strength, we know inside electric field is zero. So exactly like what we have done before.
Yeah.
This part is 0. Electric field is 0, and it is decreasing once you come out of the surface, away from the center. Yes.
Okay.
So that is the graphs we have from, like, different electric field sources. Okay. Yes.
This is one of the repeating
Yeah.
questions.
Potential and electric field
Yeah.
relation.
In the
And
same graph. Look, V and E with R in the same graph. You can check.
E is proportional to 1 by R square, and V is proportional to just 1 by R only, right? For a point charge. That is the difference between the two relations. Yes.
Check the difference in slope. E should come here. Okay.
Yeah.
So you can just by heart this shape.
Yes. It is more steep.
Okay.
Fine. And variation of potential with respect to distance from the center of a charged metallic sphere. Yes.
You can see potential is constant. Till the surface, the potential will be a constant.
See, if potential is 10 volt outside, it is 10 volt everywhere inside, right? Yes. So it is the same value till the surface. Once you come out of the surface, it decreases, inversely proportional to R, right? Right, sir? So that is what you can see in the graph.
It's not that there is difference. Like you have to read the question carefully, whether it is electric field or potential.
Exactly.
Field we already discussed, inside it is 0. Potential means you have to do, don't forget, like MCQ means similar kind of graph will be there. So there should not
Potential
be-
on the surface here.
Yes.
Okay, yeah.
Atul, it can be a sub question. We have discussed some question with a sub question of draw the graph, plot it. So such question will be there. It can come as MCQs also.
Exactly.
Okay. Yeah.
Independent questions are also possible, like, just for the graph.
All right.
Yes.
Okay.
And current electricity, when we come to current electricity resistances, VI relations, right?
VI relation. So ohmic and non-ohmic resistance. This is ohmic resistances.
Transferred to two parts,
Yeah.
one ohmic, another non-ohmic.
Yes,
So you
V
can get the
proportional to I.
erratic is it
Yes,
right there?
yeah. Fine. So V proportional to I, and here this is not linearly proportional. And we have that VI graph for one thing we have to mention here, sir, right? Semiconductors, of course.
Semiconductor.
Yes, so that VI graph will be
Semiconductor,
like.
that gallium arsenide separately
Yes,
or general semiconductor?
gallium arsenide. Also, you have to remember that term because specifically we get questions.
Question came,
Yeah,
and
gallium.
another thing, in semiconductor, you are studying that graph, no? Forward and reverse characteristics, that it is non-linear. Know that.
Exactly. So gallium arsenide, understand that is a semiconductor. That's it. Yes. Then variation of rho T graph. Yes, rho T graph. See, rho T graph is also one of the repeating graph from this part. Resistivity versus.
I have
like
already
temperature.
discussed this for copper question today.
Yeah. Yes. So
And this
it may
is-
be.
yeah.
Yeah, it may be just generally metals
Metal
or
or
conductors,
conductor
or
or-
specifically it will be given copper,
Copper, yes.
aluminium, like
Copper,
that. kind of
as the
things.
diagram is there in the reader.
Yes. So that is possible, and this we know for
Silicon,
semiconductors.
So it can be
And something we missed here is the other graph, right, sir? For alloys. So it will be going in
alloys
straight
will
line.
be
Yes,
straight line.
yes.
So you have to
VI.
go through that graph.
Yeah. Alloys, and you remember just nichrome because nichrome is specifically given.
Specifically
Yes.
given.
Nichrome is the alloy we know, so that graph will be straight line. Fine, good. Rho T graph is one of the important topic. Okay, just remember. Variation of current I versus resistance connected to a cell. Okay, this part we just mentioned during the discussion.
Today, yeah.
Yes.
So go
So
through it.
nothing more from that. Current electricity.
This one
yes.
also we discussed today.
Yes, and
Same thing.
not
Important.
once, sir. Actually, I think 2-3 questions this graph repeatedly came. There was a question to draw this graph, and also we had numerical questions related to this graph. Yes, so very important. V versus I graph. We had V versus R graph also.
That also we
Hope you remember. Yes. So the question once we explain, that weird graph.
Like this, yeah.
Yes. Okay. So remember that also. V versus I.
Graph
V versus
question,
R.
always you have to read the question carefully. That's what again and again I'm saying, you have to understand which situation they are asking. Is
Exactly.
it
Understand
B
the
with
relation
active?
first.
Yeah.
Then draw the graph.
Okay.
Fine. And yes.
Magnetic field.
Yeah, that diagram may help to understand better, right? So starting from the center, this is an application of ampere
This one,
circuital
I
law.
think we discussed in MCQ session.
Yes, one.
That MCQ challenge session,
16
this
days
how
MCQ.
this comes, we discussed it. Anyway, just
Yeah,
go through
so
that.
if you go for inside, so up to the surface, it is linearly
It's
increasing.
directly proportional.
And once you go out of this at a point P, suppose in this range, it is decreasing. Right, so that is how the graph is represented. Increasing until you come up to the surface. So on the surface, it will be maximum, then decreases. Magnetic field in a current carrying wire. Application of ampere circuital law. So only application we have the derivation.
Yeah.
See, good.
Okay, next.
Then
Not
this,
writing that. It's a repeating question.
and also
We are familiar with this. I think.
yeah, so many diagrams in this chapter. So many graphs. So the phasor diagrams, like time diagrams, like that.
Just like
XL versus omega graph, right? So this is one of the important graph, and XL versus omega, L versus omega, XE versus omega, and
I
Z
think they are
also.
familiar with this because this chapter is
Yeah.
fully based on this phasor diagram graphs and all.
So because that is what we have to learn from that. Only, especially LCR circuit, we have only phasor diagram solution. So once you're okay with that, only we can solve LCR circuit. So I think nothing more to explain from graphs. These are all the things. And remember this graph. Just the last question was based
Last
on this graph only,
question,
right?
yeah.
Yes. And our impedance triangle.
At resonance frequency, the current will be maximum.
Yes, so I think that is explained, Ali Faisal sir, well. Okay, and devices, yes. So graphs we are going to wind up now. The devices we have. Device in the sense we get repeating 3-mark questions to explain
Yeah.
working principle, construction, and working of a device. So that kind of questions we mean. This is one of the repeating one. Current, electricity, Wheatstone bridge, 3 marks. Okay, so make sure you are able to obtain that balancing condition, right? Derive balancing condition. That will be usually we get the question from this part.
By heart the final formula.
Yes, P by Q is equal
As
to
I'm
R by
always
S,
saying in the
that
class,
equation.
You have to reach there at any cost.
Yes, and applying that sign conventions properly will give you the, that derivation is not at all difficult, right, sir?
It's easy.
So very easily we can
Easy
obtain that equation, so fine. Right, and another one, yes,
Moving
another
to the
repeating
galvanometer, an
question.
important
This is
topic.
another 3-mark question, construction, working, and principle of moving coil galvanometer. Sometimes conversion too, yes, just make an idea about how it can be.
When I've studied some
Converted.
other diagram, this is a diagram which is there in a reader.
Yeah.
You study some other typing, it's fine. You just study it.
Yes, okay.
Okay.
MCG, yes, exactly. Moving coil galvanometer, that is the next device we have. Okay, so current electricity, one device, moving charges, another device. Like coming to AC generator. So the last part of induction. Actually, we usually take it along with AC, because we generate AC from this. V is equal to V0 sine omega t. Its principle, working and all. And this AC, we use it in the next chapter throughout in our devices.
Transformer also they have to.
Yes. Yeah. That I think is added. No. Yes. Yeah. Transformer also, that is an important question. Okay.
Transformer working principle.
Yes.
So what is the working principle of transformer?
Exactly. From AC.
Step down, step up. Schematic diagram of those.
Right. Okay, that's so for how many devices we mentioned so far? Wheatstone bridge. Moving coil galvanometer, generator and transformers. 4 devices from these chapters. Okay. Yes, and all these graphs. Okay. Make sure you're okay with these concepts.
I'm sure these guys, they will do it.
Yeah. First volume,
like the whole physics exam.
Yeah.
Yes or no, guys?
Yes.
What do you think?
Yeah. Then second volume tomorrow we'll be doing PN junction.
Yes. Hisham, PN junction.
Second part we'll be doing.
Exactly.
So
we'll do the same thing in the second part also at the end tomorrow.
Yeah.
And we'll just try to reduce the time of discussion, of course, because it is quite long.
Yeah.
4.5 hours now almost. Like we'll try to fix into 3 hours or 3 hours, right, sir? Because optics will be the most important topic.
Yes. So all of you should be there tomorrow also, same time. We all three will be here to discuss the second part. By that, the physics paper. See.
So 70 out of 70 by tomorrow.
Okay, so have dinner,
Fine.
like, just go for a sound sleep and go for final touch-up if you have something to do. Okay, so keep your notes safe, all questions solved. And tomorrow at 5, we'll come on live once again for part 2.
And tomorrow morning time,
else,
if they want to any patch up work, they can use the same video again. So pause it and work on it.
Whichever question you want to revise, just go through that, try it and make it perfect.
And as we reminded right in the beginning, MCQs we didn't touch in this discussion.
Yeah.
Mostly we were 2, 3 and 5 mark questions, right?
Yes.
So MCQs.
Okay, Imran. Okay, fine. Almost 12 in India.
Guys.
Okay, so it'll be our real final lap actually.
It's midnight.
So last once in a year now. So thank you for entertaining us. Okay, keeping us energetic. So
Guys, all the best. See you tomorrow. Okay.
See you tomorrow.
So don't waste.
Okay, so tomorrow at
5.
5, right, sir?
Five.
Yes.
till then,
We'll be back.
Bye.
Thank you and good night.
Hi everyone, welcome to amazing channel of Brilliant Katha.
When you are rubbing one body with another body, electrons are transferred from one object to another object. Okay, this process, this type of electricity is been given a name.
Halogen connected carbon sp3, then it's connected to benzene ring. See all of you, halogen connected. What is this carbon hybridization? Full single bond sp3, see then a benzene ring.
Denominator poles shouldn't be included in the denominator poles. That means the denominator, these -1 and -5 should never be included in the solution.
Homocircle caudal fin. It's giving 2 equal lobes. But in case of cartilage fishes, look at here, one big lobe is there, one small lobe is there. You cannot cut into 2 equal half this fin.
Brilliant Katha.